Okay. Good morning. My name is Glenn Cunningham, and I teach in the Mechanical Engineering Department at Tennessee Tech University since 1985. The workshop that we're going to be moving into is entitled Compressed Air Efficiency, and the purpose of the workshop is to try to deepen the understanding of those that go through it about the operation of the components of a compressed air system, the compressors, dryers, filters, distribution system, and end use, and to try to come up with ways to make that system more efficient, improve the maintenance performance, and reduce the operating cost. The course layout for the workshop will be comprised of an introduction where we'll make some general introductory type comments related to the relative cost of compressed air as a site utility. We'll then move into the generation of compressed air. We'll look at the three most common compressor types. That would be reciprocating, lubricant injected rotary screw, and lubricant free rotary screw, and then centrifugal air compressors. We'll then move into the conditioning of compressed air, which is primarily filtration and moisture removal. We will then have a segment on the distribution system. From the compressor room, we have to obviously distribute the air to the end users. So we'll look at velocities inside the pipe, different sizing criteria, and then we'll move into end uses of compressed air and discuss appropriate and inappropriate uses.
In the introductory section of the course, we start out with a discussion of the topics that will be covered throughout the workshop. We move on to some comments about the relative cost of compressed air compared to other energy sources used within an industrial or manufacturing plant. We look at the life cycle cost briefly of owning and operating an air compressor. We look at typical components of demand. Where does the air go that is generated by the compressors in an industrial compressed air system? We then introduce a variety of terms and make sure that we're speaking a common language as we go through the rest of the workshop. We introduce a couple of short equations that are useful to those who might be doing calculations relative to their compressed air system. We then look at a number of slides that discuss the efficiency of the overall process of compressing air from, say, atmospheric pressure or close to that to 80 to 120 pounds per square inch. We make a few comments about waste heat recovery potential for different types of air compressors. We look at an overall system layout for a typical compressed air system and look at the various components. And then we talk about measurements which you can take on a system to help you evaluate the efficiency and figure out in a fairly detailed sense how your compressed air system is operating. A more detailed list of the topics to be discussed during the workshop is presented here and on the next slide. We will look into the different types of compressors that we see in industrial settings. We will try to understand compressor controls and how they relate to the efficiency of operating the system. We'll talk a good bit about the treatment and conditioning of compressed air so that it is appropriate to the end users and that we don't accumulate blockages or moisture or corrosion inside the piping system. We will take a quick look at air receivers and storage tanks, and there's a small equation that we will talk about that will help you be able to size an air receiver tank for a particular application. We'll also look at compressor selection and sizing. Additional topics discussed during the workshop have to do with minimizing the pressure drop from the discharge of the compressor out to the end users. We also will discuss compressed air leaks and the development of a leak program to manage those leaks and try to keep them minimized over the long-term operation of the system. We'll talk a little bit about inappropriate uses for compressed air, and then we will summarize all of the discussions with a brief summary at the end of the course. While the production staff may think that compressed air is free, in reality, compressed air is usually the most expensive of the site utilities. It is not appropriate to blow off your clothing, blow off your workstation, blow off the floor, or use compressed air for anything other than a use that it absolutely is required for. While compressed air systems are expensive to operate, the cost can be minimized and controlled, but in order to do that, you have to have a plan. It's not going to happen by itself. You cannot just expect that folks are going to minimize their use of compressed air, that leaks are going to get fixed, and that inappropriate uses are going to go away unless you have a plan. Have you thought through all of the different aspects of the operation of the system, and you consistently over the long term implement that plan? We want to look at the relative cost of energy used in an industrial setting and compare the pneumatic energy delivered with compressed air to that of natural gas and electricity in general. So if we take a look at natural gas, it's today the price, small to medium facilities is on the order of $5 to $7 per million BTUs, and that would be 1,000 cubic feet. Electricity at 8 cents a kilowatt hour converts to $23.44 per million BTUs. It should be noted that it requires, on average, 7 horsepower of compressor input power to produce the compressed air needed to operate a 1 horsepower pneumatic motor. So what that means is that you can take that $23.44 and multiply it by 7, and you get a number like $164 per million BTUs of delivered energy via compressed air. So this direct comparison shows us that compressed air is typically by far the most expensive energy that you can use inside a manufacturing facility. In this slide, we're looking at the conversion of electric power to pneumatic work. That's what the air compressor does. So if we look at the bar chart, on the left-hand side, we get a bar that rises in terms of the horsepower scale to about 7.5. And so that particular bar that's all yellow is the input power to the electrical motor. Now, if the middle bar represents the shaft power that comes out of the motor that is directly coupled to the compressor inlet, and we see that's on the order of 7 horsepower. And then the final bar on the right shows the useful work, that basic 1 horsepower output in dark blue compared to the input power to the compressor. That's the 7-to-1 ratio that we've talked about. So graphically, if you look at the bar on the left, that's kind of what you're putting in and paying for. And in terms of energy, that little blue stubby bar on the right is the useful energy that you get out. So this just graphically illustrates the inefficiency of working and using compressed air. We're now looking at the life cycle cost of owning and operating an air compressor. If we look at this pie chart, we can see that the original equipment cost is roughly 12% of the overall total, and this would be the total cost of owning and operating the air compressor over 10 years. So 12% of that would be the original equipment cost. Another 12% of the total pie would be maintenance, and the remaining 76% would be the cost of the electricity that we have to purchase to put into the air compressor to operate it. So what that tells you is that if you're about to buy a new air compressor, that you need to think long and hard about how to make it as efficient as possible. Because if we up the equipment expenditure a little bit, maybe that goes to 13 or 14 or 15%, but you can shrink the electrical energy use over a 10-year period, you're going to come out way ahead of the game. So thinking about attaining the maximum possible efficiency when we purchase new air compressors and equipment for the system is a must. We're now looking at the typical components of demand. So what this slide is illustrating is where all of the compressed air that's generated at a typical industrial manufacturing concern, where that air is used, where it goes. And we can see that roughly 50% of it on average, and of course each facility is going to be different, but on average 50% of it goes to production. 25 to 30% goes to leaks. 5 to 10% goes to inappropriate uses, and 10 to 15% goes to a term that we will define on the next slide that's called artificial demand. But, I think the point here is that of the air that we generate, we typically only get useful service out of half of it. Now, if folks have a really aggressive, what we would call a world-class program, that number may go up to 65 to 70%, possibly a little bit higher, but it's very difficult to effectively use virtually all of the compressed air that you generate. This slide defines the term artificial demand. If the compressed air system pressure is, let's say, 110 psig, fairly constant, when it only needs to be, let's say, for example, 90 psig, then every open blowing application and leak exposed to full system pressure will use or pass more compressed air than it would if the system pressure were reduced to 90 pounds per square inch gauge. This extra air use is what we mean by artificial demand. By simply lowering the pressure to the minimum point that we actually need to operate the system, we can reduce the amount of air that we leak or use in open blowing applications. The next several slides we will go through some of the terms that are used in the compressed air arena, just to make sure that everybody is kind of on the same page. These terms can be defined as follows. PSIA is a pressure, pounds per square inch absolute, which means that it's measured relative to absolute zero pressure. PSIG, pounds per square inch gauge pressure, is measured relative to atmospheric pressure. CFM is cubic feet per minute of flow. ACFM is actual cubic feet per minute of flow. Inlet ICFM is inlet cubic feet per minute of flow. SCFM is standard cubic feet per minute of flow. Although the ACFM, ICFM, and SCFM simply recast the flow rate to a particular temperature and pressure. Actual could be an actual situation. Inlet could be, say, an inlet to a compressor or a filter or a different device. And standard refers to a standard temperature, pressure, and even relative humidity level. The Compressed Air and Gas Institute defines standard air as 68 degrees Fahrenheit, 14.5 pounds per square inch absolute, and completely dry with no moisture present. ASME standard conditions for air are 68 degrees Fahrenheit, 14.7 psia, and 36% relative humidity. BHP is brake horsepower. That would be the power delivered actually coming out of the shaft of a motor. For example, you might have a 50 horse motor, but it might only be pulling 30 or 35 horsepower, and that's dependent on the load that it's asked to drive. Then we have two figures of merit. One would be brake horsepower per 100 CFM, or you can call that a specific power. So what's the brake horsepower into the compressor per 100 CFM of air produced? And then we can convert that from horsepower to units of kW, and we can also cite a specific power of the kW per 100 cubic feet per minute of air produced. Here we're going to discuss more of the terms actual CFM, inlet CFM, and standard CFM. So the actual CFM is the flow rate of air at a certain point and at a certain condition at that particular point. When used for the capacity of an air compressor, it is the delivered flow rate, measured at prevailing ambient conditions of pressure, temperature, and relative humidity. Inlet CFM, ICFM, is used by compressor vendors to establish conditions in front of additional equipment like an inlet filter. When air passes through the filter, there will be some pressure drop. And standard CFM, or SCFM, flow of free air measured and converted to a standard set of reference conditions, which we saw on the previous slide. There may be confusion with this term since all standards are not the same. The Compressed Air Challenge and Compressed Air and Gas Institute have adopted the International Standards Organization ISO definition of standard air as a pressure of 14.5 psia absolute, 68 degrees Fahrenheit, and 0% relative humidity, or completely dry. This slide shows a fairly simple formula or equation that can be used to convert a flow rate of SCFM, or standard cubic feet per minute, to an actual ACFM flow rate. And so we can see that the ACFM is equal to the SCFM times, we have the first bracketed factor, which is the P standard, which is the standard absolute pressure, 14.5 for the compressed air challenge standard, divided by the P actual, the actual absolute local pressure that we're wanting to use, minus the saturation pressure, P sat, and that's the water saturation pressure at the actual temperature of the air, times phi, which is the relative humidity. So you see that bracketed factor, and then we multiply that by the temperature ratio, the actual air temperature in degrees Rankine, that has to be an absolute temperature, divided by the standard air temperature, also in degrees Rankine. So that is the conversion from an SCFM to an A or actual CFM. This slide just shows an example calculation where we are converting from 1,000, a flow rate of 1,000 standard cubic feet per minute to an actual flow rate. And so in this example, the elevation is 5,000 feet, and so the actual pressure is 12.23 pounds per square inch absolute. The actual temperature is 80 degrees Fahrenheit, which is 540 degrees Rankine. The water saturation pressure at 80 degrees Fahrenheit is 0.5069 pounds per square inch absolute. The relative humidity is taken as 80%, and then we simply plug the numbers into the previous equation, and the calculation shows that the actual CFM is 1291 compared to the standard flow rate, the SCFM of 1000. This slide begins our discussion of compression efficiency. This is kind of a generalized discussion about the overall process of compressing air. And we will consider a 125 horsepower air compressor that could easily be drawing 100 kW of input power into the motor. We'll examine the energy flows into and out of the control volume drawn around the air compressor. So kind of that's what these arrows do. We have the one on the left, we have the input power, which over the course of one day, we're going to take that to be 5,280 kilowatt hours per day. Goes into the air compressor. And then let's look at where the energy goes that comes out of the compressor. And so we're struck immediately by the amount of waste heat and other losses that represent 3,221 kilowatt hours per day. A significant amount of the total input energy goes to waste heat and frictional type losses and etc. in the air compressor. We look at leakage. It's worth about 432 kilowatt hours per day. And then we have some legitimate uses for the compressed air. For actuation, we're saying that is 62 kilowatt hours per day. For conveying, 1,092 kilowatt hours per day. And for blowing applications, including cleaning, purging, cooling, sealing, and filter pulsing, 415 kilowatt hours per day. And we have some hand tools, an air hoist, an air gun, etc. That's worth about 58 kilowatt hours per day. So if you look at what you really get out in terms of useful energy compared to what you put in, again, you get the picture that using compressed air, if it's not absolutely necessary, is not a particularly good deal from an energy cost perspective. Here we're looking at a photograph of an actual air compressor on the right, and then kind of a cartoon stick figure diagram on the left. And we'll have a series of slides here that illustrate, again, the compression efficiency of a typical air compressor. So this is just going to show kind of diagrammatically the energy flows. So we see there's the 100 kW of electrical input energy into the box of the motor, and then we have a shaft going over driving the air compressor. In slide 20, we see the addition of the motor loss to the previous figure. We still have the 100 kW electrical energy input, and now we see that the motor is 92% efficient, which means we have an 8 kW loss, which winds up as heat delivered to the space around the air compressor. Some of that is directly friction, other part is windage from the fans that cool the motor, but that entire 8 kW eventually becomes heat in the surroundings close to the compressor. We're still working on the compression efficiency series of slides. And in this slide, we have added a large arrow indicating that the desired product from the air compressor, as I think we all know, is high pressure air, which has a multitude of uses within the manufacturing and industrial facilities. In slide 22, we take note that while the desired product from the air compressor is just high pressure air, the actual product is high temperature, high pressure air. And it's going to turn out that a great deal of energy goes into producing the elevated temperatures of the discharge air, and that typically turns out to be wasted energy that winds up in the environment. All industrial air compressors have some sort of an aftercooler in order to reduce the final discharge temperature of the compressed air from the compressor itself. And in this slide, we see the addition of the heat exchanger, or the aftercooler, indicating that we are rejecting 80 kW of thermal energy to the environment. So, we see in general that the high pressure air is desired coming out of the compression element. We see high temperature, high pressure air, and then we see the rejection of 80 kW of the 100 kW that was initially input into the motor to drive the air compressor. Now, it is possible that some portion of that 80 kW of thermal energy rejection could be recovered and used for a useful purpose, but chances are it won't be. And if it is, it requires investment in additional equipment to make that happen. Slide 24 shows that we have added an air motor to the system to receive the cooled compressed air from the aftercooler. And the air motor is capable of producing typically 10 to 20 kW of shaft energy that can be used for many different purposes. You could turn a pump, you could turn a stirrer, perhaps in a painting situation, but there are lots of uses for the shaft energy. We also note that the discharge air from the air motor is typically very cold, and that explains the fact that we have not violated the first law of thermodynamics, because if you add up all of the energy flows, we say that we're putting 100 kW into the motor, and we are accounting for 8 kW of thermal loss, 80 kW of rejection, that's 88, and then between 10 to 20 kW of shaft energy, which could put us over the 100 kW that we put in the first place. And the explanation to this is that the air discharge is so cold, it has less energy input than it did when it entered the compressor, and so that would close the energy balance on the system. Slide 25 is the final one in this short series on compression efficiency, and we see the entire system with all of the energy flows that we have previously described, with the addition of two notes at the bottom of the slide. And the first one says compressed air is the most expensive common utility that would be in an industrial or manufacturing plant. And it's more expensive than natural gas, it's more expensive than electricity that's just used directly, and it requires management in order to be able to control the cost and even optimize the operation of the system. Without a concerted effort, those costs will not be minimized, and it's possible for compressed air costs to really get out of hand and can be really quite large. The recovery of waste heat from a lubricant injected or lubricant free rotary screw compressor is quite possible. In this slide, we're looking at two air-cooled compressors, pretty good size. I think those are probably 400 horsepower compressors located at a manufacturing facility actually in Knoxville, Tennessee. And what they've done is they have added fairly extensive ductwork on the air discharge from the compressors, and that carries away a good bit of, well, most of the heat of compression. And there are some movable dampers. And during the wintertime, when the plant requires heat, the dampers can be set such that warm air, even could be considered hot air, be in the range of 130 to 150 degrees, coming off of the tail end of those air compressors, is directed through that ductwork and is distributed out in the plant to provide space heat. And so that would eliminate the need to operate other conventional space heaters and would reduce the energy use for the facility. And then during the summertime, when you don't want the compressor heat inside, then the damper position is changed and the heat is ducted outside the facility. So the good part of this type of a system is during the heating season, we get to use the waste heat from the air compressors to reduce our space heating cost. Kind of the bad news is, though, that during the summer months we have to dump it to the environment and we don't get any use for it. So that can extend the payback on a project because we can't use that waste heat 12 months of the year. Water-cooled air compressors have the potential to preheat makeup water going to devices such as boilers or water heaters. On a boiler, makeup water would be expected to be someplace between maybe 70 to 80 degrees exiting the water softeners or the RO units before being introduced into the deaerator. That water could be routed through the cooling sections of an air compressor and could exit at temperatures as high as 130 to 175, which then would, when introduced into the boiler system, would reduce the amount of fuel input required by the boiler. Also, water heaters. If we have a continuous heating of cold water out of the ground, that water could be routed again through the air compressor to pick up the heat of compression, and that could drastically reduce the amount of energy input to the water heating system. It should be noted that these types of systems often can operate 12 months out of the year continuously. It could be as much as 8,760 hours per year for continuous operation. And that's much better on the payback compared to, say, the space heating described in a previous slide, where we were taking hot air on an air-cooled compressor and using it for space heat. Well, that's good in and of itself, but for most parts of the country, the heating season, especially in industrial facilities, might be 2, 3, 4, 5, 6 months, and the rest of the time we throw the waste heat away. With a water-cooled compressor, we have the potential to be able to utilize that waste heat continuously. In this slide, we have a diagram of an overall typical compressed air system. We show two lubricant-injected rotary screw compressors with the boxes just kind of lightly shaded in, so you can barely see the square cabinets that typically would enclose these. We have a dryer that obviously is used to take moisture out of the compressed air. We have an air receiver or a storage tank fairly close to the compressors, which is very typical. We're showing a pressure flow controller on this, which is a device that will attempt to maintain the downstream pressure plus or minus 1 psi of its set point, so long as we have enough air stored in that storage tank back upstream. The pressure flow controller is comprised of very rapidly acting valves that respond to changes in air pressure to try to hold it very, very close to its set point. We show a rectangular distribution system, which is good. We can feed loads from two different directions once we get past the pressure flow controller. We show a couple of different loads out in the system. There's typical, they're not really defined, I guess. We've got some folks, one of which is using a pneumatic hand tool. We show some filter, regulator, and lubricators, which are typically connected to the airline right before in end use. And we also show some secondary storage. There's a small storage tank out towards the end of the system. So we'll be talking about all of these components as we go through the remainder of the slides. But this gives you just kind of some general perspective on what an overall system might look like, what elements would be present. In order to do a good job managing a compressed air system, you must have some measurements. You must have some data to work from. It's really not possible just to go out and look at things and figure out in great detail how a compressor is operating, how a dryer is operating. You may be able to get some data to read out from the control panel on these devices, but typically we need more than that in order to do a good job managing a system. The old adage in energy management is you can't manage what you do not measure, and that is certainly true of air compressors. Things such as compressed air flow rates, system pressures, compressor power usage. We can use devices like ultrasonic leak detectors to find leaks in noisy environments or small leaks that you can't hear with the naked ear. And we need to have pressure drop measurements across filters, dryers, and all the different components that make up a system in order to be able to manage it effectively. This slide illustrates the usefulness in recording data on pressure and current on an operating air compressor in an actual situation. This was a 500 horsepower lubricant-free compressor, and it was fully loaded the entire time. Now, the top graph shows the amps drawn by one phase, and we would typically assume that all the phases are fairly equally balanced. And the bottom graph shows two pressure traces, one on the storage tank up in the compressor room, that would be the top trace, and the lower trace is way out in the system far away from the air compressors, where we're looking at kind of the pressure drop across the system. So the first thing we noticed in about the first half of these traces, and this was verified with the plant engineers, they were not operating enough air compressors. This plant was large enough that they needed more than this one 500 horsepower compressor. But this was a base-loaded machine. And what's happened is that the plant has lost air pressure. We see that coming out of the storage tank, we're between 80 and 90 pounds, where the desired pressure range is between 100 and 115. So for about the first half of this on the current trace, the air compressor is working as hard as it can, making all the air it can, but the amps are a little bit low, and that's because the pressure in the discharge line that it's forcing the air it produces, the pressure's down, and so the motor unloads a little bit. This problem was discovered, and an additional air compressor was started, and so we see the pressure then recover on the pressure traces about halfway through, and this the trim machine on this was running load unload, and all of a sudden we reestablished the typical pressure band between about 100 on the low side and 115 on the high side, and we see that sawtooth pattern on the pressure, and then we see that sawtooth pattern on the current as well. And so what that indicates on the current is that when the pressure in the system goes up to around 115, the air compressor requires more current to force its full airflow into the header or the main pipe that it's discharging into. And when the pressure falls, when the trim compressor unloads, then the pressure falls and the amperage into this fully loaded compressor falls as well. So very interesting situation, and this is the kind of information that you can get if you're continuously logging pressure and current on your operating air compressors in your system. There are different measurements that can be taken in order to determine the electrical power used by an air compressor. The best way to do this is to just use a fairly expensive power meter that will read out in kW or kilowatts directly. Oftentimes, however, lower cost clamp-on devices will measure voltage and current. The current would be measured on all three phases, A, B, and C, and then averaged. And the line-to-line voltage would be measured, for example, voltage between A, B, phases AC, and then phases BC would be taken, and that would be averaged. And then the power can be calculated from the equation you see on this slide. Volts, and that's average RMS, root mean square, voltage of the three phases, average RMS current of the three phases, times the power factor for the motor, times the square root of 3, because it's a three-phase load, divided by 1,000. Now, the issue just addressed in this slide is that if you're going to measure volts and amps, you have to have an accurate estimation of the power factor. And that can be a little bit difficult. The graph in the lower right-hand portion comes from the PSAT, Pumping System Assessment Tool software, the background information, but it is curve fits of full load motor amps, motor efficiency, and power factor for different sizes motors. And this can be used with the measured amperage and the voltage to determine a reasonable estimate of power factor that can be used in the above equation. Again, if you have the power meter at hand, well, you don't have to worry about the power factor because the meter will actually measure it for you, and most power meters will display the power factor as well as the actual kW of the motor. Slide 32 reiterates the discussion on the previous slide and shows two different photographs taken on a very good power meter. The one on the left shows the display of RMS volts and amps. That would be the phase-to-phase voltage as described previously, and then the amperage would be the RMS amps on each phase. Those could be averaged, a power factor estimated, and the kW on the motor calculated. The photo on the right shows a different screen available on the same power meter where the kW of the motor, the kilowatt power usage, is 73 kW, and the power factor is 0.783. That's very nice information, and this is by far the best way to determine the actual operating power on a motor or a motor on an air compressor as well. However, if you only have instruments that will measure the voltage in amps on the three phases, then you need to develop the capability to determine power factors accurately, and then the operating power can be easily calculated.
Very good. The next section of the workshop is entitled Compressed Air Generation, and here we're going to take a fairly detailed look at the different types of air compressors that are commonly found in manufacturing operations. The first type will be reciprocating air compressors, single action and double action compressors. Also, single and multi-stages of compression will be discussed with heat rejection in between those stages. We'll then move on to the rotary screw compressors, lubricant injected and lubricant free. And then finally, we will end up with centrifugal air compressors. We will look at part load strategies on all of these different types of machines and the efficiency of different methods of controlling the air compressor to reduce the capacity. It turns out there's a wide variety of efficiencies depending on the type of control system implemented, and that will be a point of emphasis.
There are two basic types of common industrial air compressors. Those are positive displacement machines, and then there are dynamic machines. A positive displacement machines traps air in a particular volume, and then as it moves through its cycle, it reduces the volume of that trapped air, which increases its pressure and also heats it up. A dynamic compressor is more like a fan, and a centrifugal air compressor has a very high-speed rotor or impeller that imparts a very high velocity to the air, and then the air is slowed down, and by the Bernoulli equation, if you take high-speed air and slow it down, you'll cause an increase in the pressure. So these are two fundamentally different types of compressors. Under the positive displacement, we'll look at reciprocating, single, double action, and rotary screw, lubricant injected and lubricant free. And for the dynamic, as I mentioned previously, we'll look at centrifugal air compressors briefly. Slide 36 shows an equation that can be used to calculate the required energy to operate an air compressor. If this information is known, the K, this lowercase k, is the specific heat ratio for the gas being compressed. That would be Cp over Cv. The capital V dot would be the volumetric flow rate, and the subscript lowercase I would be the inlet. So that's the V dot sub I is the inlet volumetric flow rate. The P sub I would be the inlet absolute pressure. And then in the bracketed term would be the ratio of the exit pressure to the inlet pressure, and that ratio is raised to the power K minus 1 over K, and then that whole quantity has 1 subtracted from it. That closes out the bracket term, and then we divide by the isentropic efficiency of the compressor. Slide 36 shows the same basic equation but modified a little bit in terms of the input variables. Here the work required to operate the air compressor is given in terms of m dot, the mass flow rate of air through the compressor. Cp would be the specific heat at constant pressure. Ti would be the inlet temperature. And then we have the same, inside the bracket term, we have the same exit pressure divided by inlet pressure, that ratio raised to the K minus 1 over K power, and with 1 subtracted from it, and then that result is divided by the isentropic efficiency. This slide shows a refinement of the previous two equations, and the refinement allows different compressor types to be a little more accurately modeled. The factor gamma has been added, and gamma equals 1 for a single stage reciprocating compressor. Gamma equals 2 for a double stage reciprocating compressor, and gamma equals 1.25 for a single stage oil flooded screw compressor. Here we see a schematic diagram of a single acting reciprocating air compressor. And the term single acting means that air is compressed on only one side of the piston. And so we can examine that a little bit. We see that we've got intake and suction valves and a discharge line. And so what happens is when the piston pulls back to the full left, it's sucking air through the inlet valves, the suction valve. And then when the motor pushes the piston forward, it obviously reduces the volume in the cylinder, drives the pressure up. When it gets to the pressure set point, the discharge valve opens and discharges the air into the discharge line. So the single action term refers to the fact, again, that the air is compressed on only one side of the piston. Slide 39 shows us additional information on reciprocating air compressors, and this is again looking at a single action machine. And as we've said before, we use a piston that compresses air on only one side. These machines are available in single or two-stage models. Usually they're air-cooled. Most are less than 30 horsepower, but can be as large as 100 horsepower. They tend to be very efficient, especially when these smaller machines have start-stop control, which actually, when the desired set point pressure is reached, the motor actually completely shuts down. And these are good point-of-use compressors to lower main system pressure in large plants. And what that refers to, you might have one or two small applications that require a higher pressure than the rest of the plant. And it would be expensive in terms of operating cost to raise the discharge pressure of your entire compressed air system for one or two or three small uses. And so it's better to supply a small reciprocating air compressor to provide that higher pressure air, and then run your entire system or the remainder of your system at a much lower pressure. That can drastically reduce your operating cost. And we see at the first of our specific power numbers here, we see that we would expect about 22 to 24 kW per 100 CFM of air produced out of these small single acting reciprocating compressors. The previous slide mentioned a start-stop control mode on that small reciprocating air compressor. It turns out that start-stop control is very efficient. However, only smaller motors can be operated in a start-stop mode. When a motor starts across the line, the inrush current is approximately 6 to 8 times the normal running current. This inrush current only lasts for several seconds, but it does cause short-term heating within the motor windings and elements. And when we see motors as large as 75 to 100 horsepower, they will fail prematurely if operated in a start-stop mode where we have a large number of starts and stops. So the smaller compressors can do this, and it really helps their efficiency of operation. We would like to be able to do it on larger air compressors with larger motors. However, you just shorten the motor life too much, and so that strategy is abandoned when you start approaching the 50 horsepower limit. Slide 41 is simply a photograph of a small single-acting reciprocating air compressor, and it's noted that it is air-cooled. Most of these are air-cooled. You can see the fins on the side of these cylinders. This slide shows a cross-section of a double-acting reciprocating air compressor. And the characteristic here is that as the piston moves back and forth, we actually compress air on both sides of it. So it has two sets of intake valves, two sets of discharge valves. And so no matter which way the piston is moving, on one side it's drawing in air, and on the other side it's compressing air. And then when it reverses and goes back, it does the same two operations on the opposite side of the piston. These can be very efficient machines. They're not manufactured any longer. There are still a fair number in service. And they do require a fair amount of maintenance. In slide 43, we see a photograph of a two-stage double-acting reciprocating compressor. The lines are not there, and the intercooler is not shown, but that's one possible configuration. That would be for a large air compressor. On slide 44, we are addressing double-acting reciprocating air compressors. And again, the distinguishing characteristic here is that air is compressed on both sides of the piston head as it moves back and forth. These are typically larger machines than the single-acting reciprocating. The efficiency is much better. The two-stage double-acting reciprocating compressor, we would expect a specific power usage of 15 to 16 kW per 100 CFM of air. I believe the single-acting reciprocating compressors were 22 to 24 kW per 100. So you can see the significant increase in efficiency of the double-acting machines over the single-acting machines. Capacity-wise, we can see small ones, perhaps as low as 10 SCFM up to 3,000 or more SCFM. Discharge pressures can be quite high, above 250 psig. Lubricated and lubricant-free machines were manufactured. As far as maintenance, major overhaul would be expected on a lubricated machine about every 2 years, or 16,000 hours of operation would be 2 years if they operated continuously. The lubricant-free compressors we would expect to overhaul once a year or every 8,000 hours. So the relative cost of operation is high, and we note here that they are no longer manufactured, even though they are available on the aftermarket, and a good number of large industrial manufacturing concerns still have these type of machines, and they are still in operation. Here we're addressing 4 different unloading techniques for double-acting reciprocating compressors. In the upper left-hand side, we have bypass to suction. And we can see on the diagram that there is a bypass path from the discharge of the air compressor through a controllable valve back around to the suction side. So just as the name would indicate, as the piston is delivering compressed air into the discharge line, if this valve opens, then that compressed air, or a portion of it, can be recycled directly around to the intake side of the piston. So this turns out to be an effective way to modulate the capacity in terms of the amount of air the compressor is actually putting out into the system. However, it doesn't change the amount of air compressed. We're still compressing the full load capacity of the compressor, and so the power will be 100% all of the time. We'll see some diagrams of this later, but bypass to suction is an extremely inefficient way to modulate the output capacity of your air compressor. The second technique to discuss here would be the use of clearance pockets, which is at the top on the right on this slide. A clearance pocket is an extra volume that the air compressed by the cylinder can flow into if the valve, the X on the diagram represents the valve, and if that is opened, then as the air is compressed by the piston in that side of the cylinder, instead of raising the pressure significantly and forcing the discharge valve open, it will simply flow into the clearance pocket volume, and not that, so that would unload that particular cylinder. A compressor, a two-stage compressor with clearance pockets would unload in stages. It would be either producing 100%, 75%, 50%, 25%, or 0% rated capacity as these clearance pocket valves either open or shut. Continuing on, the suction throttling figure in the lower left-hand side of the slide indicates that on the suction side, the pipe bringing air into the cylinder, there is a valve which can be modulated open or shut, which adds resistance in the suction line, which makes it more difficult to pull air into the cylinder. As the piston is pulling back, it's attempting to draw air in, and when that valve either shut or modulated, partially closed, we just don't get as much air into the cylinder. So then when we compress, that cylinder doesn't produce near as much or any compressed air out into the system. And the final approach would be suction valve unloading. And we have a mechanism by which we can hold the suction valve open. And so as the piston moves back and forth, that unloaded side of the cylinder will simply pull air in and out of the supply line on the suction side and will produce no compressed air out to the system. So that type of control would have the definite points of operation of 100%, 75%, 50%, 25%, and 0% as well. In this slide, we're comparing the relative efficiencies of the different approaches to unloading double-acting reciprocating air compressors. So the axis, the horizontal axis on these control curves shows the percent full load flow from 0% to 100%, meaning that at 100% the air compressor is producing its maximum amount of air. At 0%, it's producing no air, and in most cases, the motor is still operating other than the ideal on-off curve. On the vertical axis, we have the percent full load power that's required. So at 100%, that would be the maximum input power to the motor to operate the compressor, and obviously at 0%, the motor would be off. So then we can start from the top of the curve with the horizontal line connecting 0% full load power all the way across. There is an arrow with a tag bypass to suction. And that dark line at the top is the unloading curve, and that shows just how bad bypass to suction is, that the compressor is going to use 100% full load power no matter how much air that you produce, from 0% to 100%. So there's absolutely no reduction in energy consumption as the compressor produces less compressed air. It just doesn't get much worse than that. The second line down, the dotted line, which says suction throttle, and it's generally not utilized. And you can see why, because its efficiency is not very good. So we operate the motor continuously no matter what the output load on the compressor is. At 100% flow, we would pull 100% power. That's what you would expect. That's where all these control curves wind up at full load. But as we modulate down to 0% compressed air produced, the input power is still 75% of the full load, and we're on a straight line curve. So I guess we would say at 50% flow, we would be 87.5% power, etc. And so while we get some reduction in power as we reduce the amount of air produced, it's not very good. Okay, moving on down, then we have the curve which would be for the clearance pocket unloading or the suction valve unloading, and it's actually a pretty good curve. And so we indicate the discrete operating points. So the kind of aqua blue-green dots indicate the possible points of operation with clearance pocket unloading, and as we said, we could be 100%, 75%, 50%, 25%, or 0%. And so we would just have different amounts of time at each particular point to operate and at a point in between these. And the unloading is pretty good. So we're showing at 0% air production, we're down to 20% full load power, which doesn't sound wonderful, but it's a whole lot better than the other two options that we have discussed. And again, these are large motors typically that cannot be started and stopped repeatedly, or we will damage the motor. The next curve down is the speed control curve, and we see that if we actually had a variable frequency drive in speed control on this compressor, it would be better than the clearance pocket unloading. It looks like, we don't indicate the number, but it looks like it's probably at 0% flow might be 10 to 12% power instead of the 20% with the clearance pockets. And so it's a little bit better. These machines are older, and we don't typically see variable frequency drives on them. And of course, then the best curve would be the ideal on-off curve, where we actually just operate either at 100% full load, or we stop the motor and operate at 0% flow and 0% power. However, we can't do that because of the limited number of starts and stops on a large motor. In this slide, we see some actual electrical current data that was logged on a fairly small reciprocating air compressor. This machine was running what we call load-unload and only had two operating points. It would be producing its maximum amount of air when the compressor was loaded, and then when the high pressure on the pressure control band was reached, the machine would unload either with a a clearance pocket, or by holding the inlet valve open. And then the machine would produce no air. However, the motor would continue to run. And so you can see on the slide where the electric current when the compressor unloaded falls to, it looks like about 43 or 44 amps, and stays consistently at that level. So that's with the machine unloaded, it's producing no air. And then when the system pressure gradually falls due to usage, the compressed air continues to be used out in the facility, then with no air production, the pressure will bleed off. When the low side of the pressure band is reached, then a signal is sent to the compressor, hey, it's time to make full load compressed air capacity again. And so the machine loads, and we see the current jump up to it's about 130 to about 138 amp range. And we can see the individual piston strokes on this. This is 1 second data. These pistons can move fairly slowly back and forth, so we see each individual piston stroke, and we also see the general increasing trend in current, and that's because the pressure in the system is increasing, and as the compressor continues to put out its full load capacity, it's pushing against a system that has higher and higher pressure, and so the current has to continue to rise until the pressure right at the discharge of the compressor reaches the unload, and then the compressor unloads and the current drops precipitously down to the 43 to 44 amp range. And by looking at the timing on this, we can determine the load on the compressor as well. So what you would do is you would take the time of the entire cycle, say from load point to load point again, and then look at the amount of time that the compressor is loaded out of that, and take the load time divided by the total cycle time, and that's a pretty good estimation of the percent load on the compressor. Here we're looking at the pressures in the system for the same system that was served by the previous small reciprocating air compressor. And here we have logged the pressure right at the discharge of the compressor with a logging pressure sensor. Again, this is 1 second data, or a data point recorded every second. And we put another recording pressure sensor out at some distance in the system to get some kind of an idea what the pressure drop is from the compressor discharge to a very far point away where we might expect to see the low pressure in the system. And so you can see, we see the load-unload pattern of the air compressors, where at this time we're pumping up to, on the high side of the pressure band, about 82.5 pounds. And then we're dropping to, it looks like about 73.5, something like that, on the higher trace, which is real close to the compressors. And then out in the system, we see we've got roughly a 3 psi drop, and there's a slight shift in timing between when we see the peaks at the right outside the compressor to this location out in the system. So this is really good information to use and let you understand in great detail what's going on in your system. Here we're looking at a blow-up on some of the electrical current data that was recorded on the small reciprocating air compressor. We're looking at 1.5 load cycles, and we can see, starting on the far left of this curve, that the compressor loads and stays loaded for approximately 36 seconds, which time it unloads and stays unloaded for 36 seconds. So if I look at that one particular cycle, the load time divided by the total cycle time is going to be 50%. And so for that one cycle, this compressor was putting out 50% of its rated capacity. Now, you can see the second load cycle, which is 85 seconds in length, looks like that the load has changed. And so, you know, this method of calculating the load on the compressor, you need to take a fairly large number of cycles in order to get an idea over, say, the course of an hour or a day, what percent time the compressor is loaded, i.e. what percent of rated load it puts out on average. But you can also look at different portions of the day where the load may be higher or lower and get an idea if this one compressor is grossly oversized or perhaps undersized. If it's undersized, what we'll see is it will run continuously, and perhaps the system pressure might fall. So if you had pressure data logged for the same period of time, you can see if the machine or machines in operation were capable of maintaining consistent system pressure throughout different load levels on the facility. Here we've actually calculated the percent load on the compressors, and like I said previously, for the first load and unload cycle, they're roughly equal in time length. So we had 36 seconds loaded divided by 72 seconds total cycle time times 100, that gives 50% load. If I look at the unload cycle and then the large load cycle as being one complete time cycle, then I see that I have 85 seconds for the longer loaded cycle divided by 121, which would be that total cycle time, the 85 plus the 36, and so that calculates out to 72% loaded. So we see that the compressed air demand went up for this second cycle, and the calculation shows that instead of 50% loaded, we've picked up 20% compressor load just almost very quickly, because this is a fairly short time window. Here we're looking at the pressure traces for the same system, and this is just a blow up to show more characteristics of just a couple of cycles. And we see what we had described previously. We're unloading these compressors at 82.5 pounds, and we're loading them back at a little over, looks like 73 pounds. You can see the timing involved, and we see the response out towards the end of the system, where we've got a 2 to 3 pound pressure drop. We're now going to move on to the discussion of rotary screw air compressors. And the way these operate is we have a male and a female rotors that intermesh, and there's an inlet typically on the top, and the air is drawn in and enters a cavity between these two rotors, and as they spin, the air is forced down into the space between the male and female rotors, and the volume is reduced, and as it reaches the far end, there's a discharge port typically on the bottom, and the air has reached some increase in temperature as well as pressure, and then it exits from the bottom. On a lubricant injected machine, compressor oil or synthetic lubricant is sprayed in at the inlet where the air enters the spaces between the two lobes, and then all of that travels at the exit of the machine to the air oil separator, where then the compressed air is separated from the lubricant. The lubricant is cooled and returned and recycled and reused. There are also lubricant-free rotary screw air compressors, and those obviously don't have any lubricant sprayed. The rotors are usually Teflon coated to help reduce friction. Those machines produce somewhat higher discharge air temperatures and are not quite as efficient as the lubricant injected machines. Lubricant injected rotary screw compressors. Here, as we said on the previous slide, lubricant is injected with the inlet air entering into the screws. Lubricant actually fulfills three functions. It provides cooling, it lubricates, reduces friction as the screws turn, and also seals the screws to keep the air from leaking along the axial dimension of the screws. The lubricant is removed from the compressed air by the air oil separator. Hot lubricant is cooled by a heat exchanger before returning to the sump. These compressors can be cooled with either air or water, and heat recovery is certainly possible, as we discussed earlier. Lubricant-free rotary screw air compressors are also available. In this case, the screws are Teflon coated to reduce friction, and obviously by the name, no lubricant is injected into the air while it's being compressed. Compressors can be air or water cooled. Heat is rejected from these lubricant-free compressors at a higher temperature than the lubricant injected machines. They are not as efficient as the lubricant injected compressors. They do offer good heat recovery potential because of the higher temperatures of the air at the discharge of the element. The lubricant injected rotary screw air compressor is the most common air compressor used by industrial and manufacturing sites today. Most of them are over 10 horsepower. I would say typically we see 30 horsepower up to 500-600 horsepower. The most common range would be probably from 75 to 100 up to 400 horsepower. As we said before, there are male and female rotors that trap the air and reduce the volume as they spin, spits it out the bottom side. The lubricant is injected for the purposes of sealing, cooling, and lubricating. And the specific power on these machines is typically 18 to 19 kW per 100 CFM, SCFM of air into the machine. And this would be a full load number That number is going to increase at part load, and how much it increases depends upon the unloading strategy and technology that's incorporated with that particular compressor. Here we're looking at a schematic diagram of the flows associated with a lubricant-injected rotary screw air compressor. If we look at the compressor itself, we see inlet air that would be entering the compressor, and of course that would be from an inlet air filter that would filter out particulates and things to protect the compression elements. We also are injecting oil from the lubricant manifold, which is sprayed in to the inlet air as it enters. And then we have two supply lines going to the inlet bearing shaft seal and outlet bearings to keep those lubricated on the compressor. And the main discharge from the compressor would be the lubricant and the air that goes to the air lubricant separator. There's a scavenger line that feeds a little bit of oil back to the compressor. That's a fairly minor flow. The majority of the lubricant, once separated, flows back down through a lube pump. There is thermal control by means of a bypass valve, and so the oil can go through the lube cooler or can be bypassed around it to control the temperature that is supplied back to the machine. And then the lubricant goes through a filter before it enters the lube manifold and then enters the compressor again. The discharge air goes through the aftercooler beyond the air lubricant separator. The aftercooler is not shown on this diagram. This is a second schematic diagram of a lubricant injected rotary screw air compressor, somewhat similar to the previous one. It shows the oil cooler and the air cooler, but to follow our way through the system, we see a two-stage inlet gas filter on kind of top of the compressor screws themselves. That's where the air comes into the system. It is filtered, goes into the screws, comes out the bottom of the screws, and we have oily outlet gas, or air typically. It goes into the gas oil separator, and we see we have the oil separation element, and these have to be changed on a regular basis. The compressed gas then goes over to the air cooling element, or the radiator, whereby we have a fan that's blowing air across that to cool it down. So that would be the aftercooler on this machine. Then back to the gas oil separator, we see the hot separated oil going to the oil cooler, which is also kind of a separate section in the radiator where the fan is blowing ambient air across there to carry the heat away. It goes through the oil filter and then returns to the compressor. On slide 58, we're looking at some typical manufacturer's data supplied on a family of lubricant injected rotary screw compressors. Doesn't really matter which manufacturer it is. They all have similar information. So we see a range of model numbers and sizes. As we go down, they get larger. And we see that the first two can operate at 50 hertz, and the remaining units are 60 hertz units. So, outside the United States, there are plenty of places in the world where the electrical supply is 50 hertz instead of 60 hertz. We see the rated pressure in pounds per square inch gauge. The first two 109, and the remaining compressors are 125. We see the nominal horsepower on the motor. We see the amount of airflow at rated capacity in terms of cubic feet per minute. That is, of course, the inlet airflow condition. When it's compressed, it is much smaller in volume. We see the specific power, the horsepower per 100 CFM, and then we convert that to kW per 100 CFM of inlet flow. We just see those numbers. And down at the bottom of the slide, there's an example. The EP300 is a 300 horsepower machine, which calculates out to 225 kW, and the rated airflow is 1252 CFM. So if I divide the 1252 by 100, that would give me the number of units of 100 CFM, and then I divide that into the 225, and I see the number comes out 17.9. And on our previous slides, we said that that number would be between 17 and 18 would be a typical value. And so that just shows kind of doing the calculation from some general specifications from the manufacturer. In this slide, we're looking at three different compressor capacity control technologies for the lubricant injected or lubricant free rotary screw compressors. And the first one is the start-stop, and this would be the same as described for the reciprocating compressor, where we would simply have a pressure band, and when the measured pressure right at the discharge of the compressor is less than the maximum set point at the top of the pressure band, the compressor would run. Air would be produced, discharged into the system. As the pressure in the system builds, it would finally hit the high level set point on the pressure band, and the compressor would completely shut down in this case. So this type operation would put many starts and stops on the motor, and again, unless it's a fairly small motor, 5, 10, 15, maybe 20 horse, you would damage the motor and you could not operate larger compressors with start-stop control. The load-unload also has a pressure band and operates in a similar fashion. The difference is when we hit the high pressure at the top of the pressure band, the compressor unloads, but the motor continues to turn. And we would typically expect to see 20-25% of the full load power of the motor consumed in the unloaded condition. And then the last would be modulating control, or modulation as it's known, and this typically has a butterfly valve right at the inlet to the air compressor, which kind of rocks back and forth, that adds or subtracts resistance to the airflow, and so allows more or less air into the suction side of the air compressor, and that will modulate its output capacity. In the completely unloaded condition with modulation, we still typically see about 75% of full load power into the motor, so it's not a very efficient way to unload an air compressor. In slide 60, we are introducing three additional types of compressor capacity control for lubricant injected and lubricant free rotary screw air compressors. The first one is dual, or auto dual as it's known, and this is really kind of the combination or marrying two different control strategies together. An example could be running load unload, and then if the compressor was to remain unloaded for a preset amount of time, there would be a timer built into the control system. Then the control system might shut the motor down completely and let it sit there dead in the water. Again, one would have to be careful with this to make sure that we monitored the number of motor starts so that we weren't shortening the motor life. Then we have variable displacement. This is known as a slider valve, and what this does, it effectively will adjust the length of the screws. The slider valve will change the point at which air is injected between the screws, and by changing the relative length of the active portion of the screw length that's actually compressing air, we can change the capacity of the air compressor. This actually is a fairly old technology, and it's fairly efficient. It does add some cost to the compressor, and we don't see a whole lot of machines with this on it, but you do see this every once in a while, and the unloading curve is pretty good. And then the last would be the variable speed air compressor, and these days that would mean that an inverter or a variable frequency drive has been outfitted with the compressor, and we simply change capacity by changing the speed of the screws with the variable frequency drive. This is, again, a very efficient way to unload an air compressor, and VSD machines, or variable frequency drive machines, make excellent trim machines for an air compressor system. Here we're looking at a depiction of modulation control or suction throttling capacity control on a lubricant injected rotary screw air compressor. And we have a series of three diagrams that show different stages of control, or different capacities of output of the machine. In the first one, the highest one on the top left, we would see the machine would be wide open, and that little butterfly valve in the suction pipe, or the intake to the compressor, is parallel to the flow, showing that it is wide open, allowing the maximum amount of air into the air compressor, so it will produce the maximum amount of compressed air out to the system. And then in the middle picture, in the middle of the slide, we see that that valve is partially closed, so that we would be then modulating back the amount of air produced by the air compressor in response to a discharge pressure signal at the discharge of the compressor. And then the final slide on the lower right, we see that that suction valve is closed completely, and we have unloaded the compressor, and so the motor is still running, but we are not producing any compressed air out to the system. There is a small amount of air which still is made, but it is required to continue to circulate lubricant through the machine, but it is a very small amount, and that is one reason that the current does not fall to as much as it might otherwise, because we do have to protect the internals on the compressor, even though we're not effectively producing any compressed air for the distribution system. This is a photograph of the modulation valve for suction throttling or modulation control. This is right at the inlet to the screws on a lubricant injected rotary screw air compressor. And we can see this is actually an operating air compressor, and you can see that this that valve is ever so slightly tilted, and so it is just very, very slightly open. And you notice the hole in this, and the hole is to provide a little bit of inlet air when the machine is completely unloaded to move the oil through the machine. But this is what it looks like, and then the inlet air filter sits down on top of this. You can see kind of the brackets that help hold that inlet air filter, and then there's a housing that covers up the inlet air filter. It's kind of like on the old air cleaners on the cars back 15 or 20 years ago. We just take a wing nut off and lift the top out, and lift the filter element out, change it or inspect it, put a new one in, and then put all that housing back together and put the wing nut back on. A lot of air compressors still look like that today. In slide 63, we're looking at load-unload capacity control, and this particular picture shows the unloaded condition on a lubricant-injected rotary screw compressor, and we can tell that by the inlet valve is completely perpendicular to the axial direction on the inlet pipe, indicating that it is closed off. And we see that the little red line indicating the valve doesn't extend completely across the pipe. That's that little hole that we saw on the previous slide to indicate that we allow just a very small amount of air into the compressor to continually lubricate it. The valve on the discharge line is shut, and we show this little valve on the discharge line with the black controller box, and what this is a bleed valve that allows us to slowly bleed the pressure off of the air-oil separator when the compressor unloads. We cannot dump that valve wide open. We can't allow that pressure to go to zero instantly, or the oil within the air-oil separator will foam it will cause bubbles to occur in it, and then when the compressor loads again on the next subsequent load cycle, all those bubbles will be blown out into the distribution system, and it won't take very long to completely evacuate all the oil from your air compressor, and it will be someplace out in your piping distribution system. So the manufacturers all have this set somewhat differently, but typically about 40 seconds. There's a timing mechanism, and that vent valve is slowly cracked open to blow the pressure off of that sump in 40 seconds. We also see that the motor amps does not fall completely to its minimum level until we get the pressure off of that sump. And because we have a small amount of air that's still being compressed by the compressor even when it's unloaded, and so we need to unload the machine for much more than 40 seconds or so to get the maximum benefit in terms of minimizing the power consumption for load-unload control. And the ability to do that is basically controlled by the amount of compressed air storage in the system. If we have a lot of storage, then when the compressor unloads, it can stay unloaded for a significant length of time, and we can allow the inlet power on the motor to fall to its minimum level and stay there for a significant portion of time. If the compressor is loading and unloading every 20 or 30 seconds, the power never gets to its minimum level, and we don't achieve as efficient operation with load unload as we could if there was adequate storage in the system. Here we're looking at the current recorded on a small lubricant injected rotary screw air compressor that's operating under load unload capacity control, and we've got several points designated and different tags put on those. We see where the compressor unloads, and so we see that the electrical current was slowly increasing as the compressor was producing its full load capacity. And again, the increasing current along the top of that is because the pressure in the system is going up, requiring a little more work by the motor to force the air into the system. When the discharge pressure at the exit pipe on the compressor reaches the unload pressure, the machine unloads, and we see that about the first half of that precipitous drop, it falls close to instantly. And then there's kind of a bend or an elbow about halfway down, and that's where from the initial unload that we start to bleed the pressure off of the sump, and we see that the current continues to fall, but not at as rapid a rate as the sump pressure continues to be reduced. And unfortunately for this cycle, it didn't stay unloaded long enough to reach the absolute minimum because of the demand on the system relative to the amount of compressed air storage in the system. The pressure dropped quickly, and we hit the minimum pressure on the pressure band, and the compressor controls told the compressor, hey, I need air because I'm at the bottom of my pressure band, and so the compressor loads again. So again, we see a rapid spike upward. And then, so the compressor is producing its full load capacity, and then we see the current on the machine continue to ramp up until it unloads again, indicating the pressure in the system is increasing. Over on the right-hand side, we see a cycle where the compressed air demand was much less, and the machine was able to stay unloaded for a greater length of time. And here we see the current was able to fall to 30 amps, whereas on the previous cycles it was only able to fall to between 36 and 37 amps. And so that's what happens as we finally, if we can stay unloaded long enough to get the pressure off of the sump, we'll get the current and the power into the motor down to its minimum level. Even for the cycle on the right, we needed much more storage in this system to allow it to become more efficient in terms of capacity control. We would like to see that unload portion of the cycle extend out to 2 minutes or longer in order to really help the overall efficiency of the machine. This is an electrical current trace or data recorded on a different lubricant-injected rotary screw air compressor. And here we see a series of load-unload cycles where, again, for the majority of the cycles, there's not adequate storage in the system to allow the compressor to unload long enough to get the sump blown down and to see the power fall to its minimum level. And there is the long cycle in the center is a period that could be break or lunch. That's probably a lunch situation where the compressed air demand really fell, or the storage was larger compared to the output of the machine. Whichever way you want to look at it, it's really the same situation. We see that the machine was able to stay unloaded for a significant length of time, several minutes, and then we see how the power fell to its minimum level and stayed there. So we're dropping to probably 47, 48 amps on the long unload cycle, whereas before we were getting down to, say, 58 or 59 amps. So what you would like to see is enough storage capacity, receivers in the system, to allow every cycle to look like the one large cycle in the center, where once the compressor gets the system charged up to the unload pressure on the pressure band and the compressor unloads, it can stay unloaded. And the rule of thumb is 2 minutes, that you need to stay unloaded at least 2 minutes, preferably even longer is nice, in order to really enhance the efficiency of the load-unload capacity control strategy. It's quite possible to go out and shop around for very large receiver tanks from other businesses that might be selling one. Sometimes a plant goes out of business. In general, you can't have too much receiver capacity in a system. More is always better. The question is just how much are you going to have to pay for it? What's the payback on the project? This slide shows load-unload cycles. Again, this would be the amps on yet a different lubricant-injected rotary screw compressor. We can see this is a good size machine. We're hitting up around 290 amps. And I see this is a 450 horsepower machine, and it is an Ingersoll-Rand machine. Typically I'm not going to talk about manufacturers, but Ingersoll-Rand has kind of an interesting twist on their load and unload. And if you look at these current traces, we see that when the machine loads, we see a spike in power, and then on the other traces we've seen the current continued to increase as the pressure went up in the system to the point that we would then discharge. However, what Ingersoll-Rand does, they have an option on their load-unload to use the inlet valve to modulate the capacity of the machine a certain amount in order to extend out the cycles. And this is a feature to keep the machine from short cycling too much. And so if that wasn't there, the machine would stay loaded for a shorter period of time, and then we would simply have a more rapid rate of loading and unloading cycles. So that kind of extends out the operating period by slightly reducing the capacity of the machine while the pressure in the system is still rising. So that's kind of an interesting option here. We'll see a blow-up of this on the next slide. Again, as was described in the previous slide, we see that when this lubricant-injected rotary screw compressor loads, which means the pressure hit the low point of its pressure band, the current jumps up, but once the machine gets fully loaded, then we see the current slowly erode away a little bit as the machine continues to operate. And the only way this can happen is if we are modulating back the capacity a little bit in order to extend out this load cycle. And so that's what we're seeing. We know that the pressure is increasing in the system because eventually the machine unloads, and the only way the machine's going to unload is if it finally reaches the high point of its pressure band. But for the current to fall while the pressure is building, we have to be producing somewhat less airflow. And so this is, again, an option of Ingersoll Rand compressors. That's the only manufacturer I'm aware of that does this. There may be some others. On this slide, we continue to investigate the part load operation of this 450 horsepower Ingersoll Rand lubricant injected rotary screw compressor, and it is operating again under load unload control for capacity modulation. As we look at this graph of the current on one phase of the electrical power being supplied to the motor, we see initially we're pretty constant at about 280 amps into the machine. This goes on for a period of time, about a minute and a half, and then the machine unloads, indicating that the pressure in the system has hit the high pressure or the unload pressure in the control band. The electric current and power into the compressor falls very quickly. It falls to about 192 or 93 amps almost instantaneously. And then it continues to trail off at not quite as rapid rate down to about 140, that's probably 142 amps down on the low side of the scale. It takes about 25 seconds for this to occur, and then the pressure in the system hits the low point of the pressure band and the compressor loads again. It looks like, again, the unload portion of this first cycle is about 25 seconds. Then the machine loads almost instantaneously, not quite. It takes a number of seconds, 3, 4, 5 seconds for the current to hit its maximum level of about 191 amps. And then the machine continues to stay loaded for a period well over 3 minutes. We can see the vertical grid lines are 1 minute apart, and we see 1, 2, 3, and probably 7, 8, 9 seconds on top of the 3 minutes that the machine is loaded. The current erodes slowly during this period because this is the Ingersoll Rand control option that uses modulation to reduce the capacity of the machine a small amount while it is still loaded, and this is done to prolong the loading portions of the cycle and prevent the machine from short cycling. And it obviously is effective. We have, a very good load time on this. Can also be noted the second unload cycle appears to be a little bit longer, and we notice that the current falls to right on the 140 amp line. And so that just shows that the longer the sump is blowing down, the lower the pressure in the sump, and the lower the pressure, or the lower the current required by the motor. The rule of thumb is it's about 40 to 45 seconds to get all of the pressure off of the sump. So, and these unload cycles we're seeing here, the machine never really reaches the minimum possible power input, which would be with the pressure completely off the sump and the machine producing no air to the system, but the motor continuing to run, which it has to, because you can't just turn on and off a 450 horsepower motor every 2 or 3 or 4 or 5 minutes. It won't take but a couple of weeks or a month before the motor will fail. So we have to keep the motor running. But if we had more storage in the system, then these unload cycles could last longer, and the efficiency, the part load efficiency of the machine would improve. The rule of thumb is for really efficient load-unload operation, we would like to see the unload portions of the cycle at least 2 minutes. And so you can see we're getting someplace in the order of 25 to 30 seconds. And so a potential project would be to add storage to this system in order to increase its part load efficiency. And we'll discuss that more later in the workshop. In this slide, we're looking at a variety of unloading techniques that can be applied to rotary screw air compressors. These actual curves relate to a lubricant-free machine, and we'll discuss the differences. There's really only one curve that changes or potentially changes for a lubricant-injected machine. But we'll get to that a little bit later in the discussion. So if we look at this, the bottom axis or x-axis is percent capacity on the machine from 0 to 100% of the rated amount of compressed air the machine can generate based on its size. And on the vertical axis, we see that's the percent power input. And of course, at 100% capacity on the machine, we're going to pull 100% power pretty much no matter which strategy that we use. Okay, so looking at the top control curve, which is curve A, listed as modulation control, that's that inlet, that's that butterfly damper at the inlet to the compressor that rocks back and forth and basically adds additional pressure drop on the inlet side of the system, bringing air into the air compressor. The more that butterfly damper closes, the more pressure resistance, and so we let less airflow into the machine, so we reduce its capacity. That's the good news, and for capacity control, it works great. For efficiency, it's not so good, because if you look at the completely unloaded condition, the 0% capacity, and go up to the percent power input, we're at 70%. Well, gosh, so here we're operating our air compressor, getting no useful air into the system because at that time the system's satisfied, and we're still paying for 70% of the full load power. Not a very good deal in terms of the cost of operating the air compressor. The dash line that attaches into the A curve at 40% capacity that runs down to 25% power at 0% capacity, that's an option to unload the machine. And so you can, that's kind of what's called an auto dual cycle, where you would use modulation down to about 40%, and then if the pressure continued to rise and you were on that control scheme, you would just unload the machine. And so then it would be 0% capacity at 25% power. That would be an improvement. The question is, I guess, do you have enough storage in the system to allow the compressor to stay unloaded long enough to make it worthwhile? Now, on a lubricant-free machine, the power will drop to that 25% instantly. It's just a question of if you don't have much storage, the machine will load and unload a lot, and that can cause additional maintenance issues and costs after a period of time. The curve B is active rotor length adjustment. You can buy compressors that have what they call a slider valve that basically adjusts the point at which air is allowed to enter the screws. And if you basically shorten the effective rotor length, then you adjust the capacity of the machine. And so you can see as we go from 100% capacity downward to about 45% capacity, that's a pretty good unload curve. That's not bad at all. And then once we get to 40% capacity, that machine would then operate load unload, as we just described for curve A above. Curve C is pure load unload, where the compressor really only operates at 2 points. It operates in the loaded condition at 100% capacity, 100% power. for whatever period of time until we hit the high point of the pressure band, and then the machine unloads and it drops to the 0% capacity, 25% power. And so as we move on the curve by just changing the proportion of time that we spend loaded and unloaded. Now, this nice straight curve between these points is for a lubricant-free machine. A lubricant-injected machine, we'll see on the next slide, requires a lot of storage to be able to operate on that straight line curve between the 100% point and the 0% capacity, 25% capacity. That's the best you can do with load-unload control. But with a lubricant-injected machine, because of the time required to blow down the sump, we have to have a lot of storage capacity to let the machine stay unloaded long enough to achieve a reduction in energy. Then the final curve is the variable speed compressor achieved with the addition of a variable frequency drive to the compressor package. And we can see that's a great way to unload your air compressor. It's by far the most efficient. And we see that from the 100% point down to, looks like this curve goes load-unload at about 18% capacity. And then the dashed line at the end of it, that's operating load-unload at the end. The good part of this is you don't have to worry about the compressor short cycling, because with a variable frequency drive, when the machine restarts, it doesn't just slam on like all of the other compressors do, where you just started across the line. This thing, it has effectively a soft starter built into it as part of the drive operation, and it ramps up very slowly. So we can go through the load-unload cycles on a variable speed machine as many times as we want to, and it doesn't affect the longevity of the motor. And so that's another benefit. But we see that there are significant savings for a variable speed machine, especially if you're operating 20, 30, 40, 50, 60% in that range, compared to any of the other control strategies. But the next best one would be load-unload, assuming that we have sufficient storage capacity. Here we have another lubricant-injected rotary screw compressor. I don't have the horsepower rating on this one. We see that the current's peaking out. Looks like about 168, 69 amps, something like that. So we could easily do a calculation to determine probably a 200 horsepower, but I would need to check that before I was 100% sure. At any rate, we see the machine as it continues to load into the load portions of the cycle. Now we see the current slowly increase. So over on the left-hand side of the curve, when we first start looking at this current trace, we see we're about 161, 162 amps. And as the pressure builds in the system, we're now ramping up to about 163, maybe pushing 164 amps before the compressor unloads. And so there's no capacity modulation going on here. The machine's producing all the air it can, and the current goes up slightly because the pressure in the system that it's pushing that air into is increasing, and so the motor has to work a little bit harder, and we see that in the amps. Once the unload pressure is reached, again, the current falls quickly to about 100 and looks like 108 or 109 amps, and then continues to trail off at a decreasing rate. And again, that's because the sump is blowing down. And so that's pretty much what's displayed here. Again, we could calculate the percent load on the machine by the loaded time in a cycle divided by the total cycle time between unloading points. Here we're again looking at the operation of a lubricant-injected rotary screw air compressor. This is a 100 horsepower unit, and we can see that the machine is loading and unloading several times per minute. The darker vertical grid lines on the horizontal axis, the lines going up and down, are spaced 1 minute apart. And we see that we probably have 10 to 15 seconds of unload time and roughly the same load time, maybe a little bit longer on the load depending on the cycle, but that's indicating that the machine is putting out roughly 50% airflow. And then we get up to what is, I believe, lunchtime or a break in production. And we see what's happened is the compressed air demand has gone down. We have a constant amount of storage in the system, but with lower air production rates, it makes the storage more effective in allowing the compressor to stay unloaded. And so we see then that the large unload cycle in the center, a number of interesting characteristics of the machine. First of all, we see the current fall to its absolute minimum level, which looks to be about 46 or 47 amps. Whereas on the shorter unload cycles, we were getting just below 60, maybe to 57 to 58 amps on the lowest portion of the current draw. And so that shows that if we allow the compressor to unload long enough, the sump does eventually get the pressure blown off of it and the amps reach their absolute minimum value. Once it's unloaded, we see down at the bottom of that unload trace that the current continues to fall just a little bit, and that's probably because the pressure in the system. The compressor does produce a very small amount of air, mostly for internal circulation of lubricant, even when it's not producing much for the system. But I think that's probably the influence of the system pressure on the operation of the machine when it's unloaded. Again, we see this is that during the load portion of the cycle, the current continues to increase as we move up through the pressure band to the unload point, indicating we're not doing any sort of modulation like some of the Ingersoll Rand machines did in earlier slides. Here in slide 72, we're looking at the operation of a lubricant-injected rotary screw air compressor utilizing load-unload capacity control. And what we see here is the influence on the unloading curve based on the amount of storage in the system. This would be compressed air receiver tanks or storage. And we have 4 different curves. The lowest or bottom curve is the one for 10 gallons per CFM, and that would be for the trim air compressor. That's in terms of the maximum capacity of air that the machine can produce. Let's say if that machine was rated for, let's say it's a 100 horsepower machine. It's rated for maybe 430 CFM, so we would need 10 times that. So what's that, 4,300 gallons of storage, and that needs to be fairly close to the compressor itself to let it be as effective as possible. Storage way out at the end of the system still helps a little bit, but it's not as effective as far as the unload efficiency of the machine as if it's up very close to the compressor itself. So that would be about the best that you're going to find. Not many systems have 10 gallons per CFM. And you can see that bottom curve approximates that straight line between the 100%, 100% and the 0%, 25% that we saw on the previous unload curve. Now, let's look at the top curve there, and that's a very poor situation in terms of the amount of compressed air storage in the system to run load-unload capacity control on a lubricant-injected compressor. And you see the influence, and that's the reason the curve bows up and requires more power is that when the compressor unloads, it just can't stay unloaded long enough to get the sump blown down so that the power level can fall. So that's going to contribute to short cycling on the machine, which is going to contribute in the long term to higher maintenance cost. And it's just not as efficient as having a large amount of storage. The old rule of thumb, the adage is that compressed air storage can never hurt you. Depends on the compressor type and all as to how much it actually helps, but it will smooth out pressure fluctuations. And it always helps the operation of your compressors to have a significant amount of storage in the system. And then the other two curves are just different amounts of storage in between the maximum of 10 gallons per CFM and the minimum of 1. There's a curve for 3 gallons per CFM and a curve for 5 gallons per CFM. So the real recommended number is 10 gallons per CFM. We're pretty happy when we see 5 gallons per CFM. And based on the way systems were sized a long time ago, if the system's been out there a while and you go up to do an analysis on it, you're probably going to see more in the order of 1 gallon per CFM. We are reiterating the discussion on the previous slide here just to emphasize the point that to operate a lubricant-injected rotary screw machine really efficiently with load-unload control, we require between 5 and 10 gallons per CFM of storage capacity to allow the machine to unload for a long enough period of time that the overall average power consumption will fall close to its minimum possible level. In this slide, we're discussing some of the details related to the operation of a variable speed air compressor. The first bullet says air end displacement is directly proportional to rotor speed, but best air end efficiency is at 1 optimum male rotor tip speed. What that means is that when the compressor designers put the screws together or they design the optimum operation of the screws, they have to pick one particular speed. And what turns out is that on a machine that's intended for baseload operation, i.e. producing 100% rated capacity on the compressor, that optimum tip speed will be for maximum capacity at 100% load. When the variable speed machines, the rotors are designed, the optimum tip speed is much less than the 100% capacity point. And this is because the machine is expected to be a trim machine. That's the real reason that we would want to outfit it with a variable frequency drive, is to get the enhanced efficiency at part load. And so they're going to make the machine even more efficiency at part load by optimizing the screws to be most efficient at the 40 to 60 to 70% load range, in the middle of the load range, instead of at the 100% capacity load, which is where you would want a constant speed air compressor to be optimized, hoping that that machine would operate at 100% load, which is really what it's intended for. So what this says is that if you have a variable speed air compressor, you don't want to operate it at 90 to 100% load very much of the time. It's going to cost you two ways. First of all, it's going to cost you because the screws are not optimized at those higher capacities, and also the variable frequency drive has electrical losses in it. And so you don't, if you're going to operate it at 100% load, it's going to cost you more than just a standard constant speed air compressor of the same size at 100% load, because that machine is optimized for 100% load, and the variable speed machine is really designed and intended to be operated at 20 to up to maybe 75 or 80% load, but probably in the 40 to 60 to 70% range. In this slide, we're continuing the discussion of the variable speed air compressor and comparing, contrasting to constant speed compressors and the design of the screws. And the curve here illustrates the fact that on the constant speed air compressor, the screws are optimized for a fairly narrow range of speeds, because it's going to operate at essentially the same speed all of the time. The only difference in speed is going to be caused by the slip on the induction motor, and as we load an induction motor to its rated output capacity, we have the maximum slip in terms of the difference between the synchronous driving field, electrical field in the motor, and the actual rotor rotational speed. And as if we unload the motor a little bit, the slip declines and the motor increases speed a small amount. For example, a motor, a 4-pole electrical motor, would have a synchronous speed of 1800 RPM. At putting out its rated load, it might be rated for 1750, 1740, something in that range. If you operate it at 25% load, the speed will increase a little bit, say to 1770, 1775, depending on the particulars of your motor. But the speed doesn't change much, so the screws don't have to be optimized over a very wide range of rotational speeds. On the variable speed air end, we see that those screws are optimized over a much wider range of speeds because that's the purpose of adding the variable frequency drive to the compressor package, is to achieve a wide variation in rotational speeds, and that's how we're going to control the capacity. The constant speed machine has some of these other techniques for capacity control that we've already discussed, like load unload or modulation, etc. It also brings up the point that it's difficult to get the optimal efficiency out of a constant speed air compressor by retrofitting a variable frequency drive to it. Now, that electrically that can be done, and there certainly are savings related to it. The compressor manufacturers certainly don't like it. If you had any sort of a warranty out there on the machine, I'm sure it would void it. And it would not be as efficient as buying a new air compressor where the entire package has designed to be a variable speed machine. So you'll get some blowback from the manufacturers if you call them up and discuss adding a variable frequency drive to one of your constant speed air compressors. In slide 76, we're showing a picture of a Gardner Denver variable speed air compressor with some points indicated, numbers 1 through 7. Some of this is a little bit of marketing literature here, I believe, but anyway, you can read and see what's being discussed, noise levels, etc. The point to discuss here is just to drive home that the variable speed air compressor needs to be the trim compressor in the system. We really, if we're operating 3 or 4 air compressors, we really don't want to be operating 3 or 4 variable speed air compressors. The rule of thumb in compressor loading is if you have multiple compressors in operation, you want one trim machine and you want every other compressor operating at 100% rated load. The most efficient operating point for an air compressor, well, is really off. But for an operating air compressor, the most efficient point is 100% load unless it's a variable speed machine. So if we've got 3, 4, 5 compressors in operation, we would want to have some sort of a smart sequencer that could operate the proper mix of machines so that we had every machine 100% loaded except the trim machine, which would be a variable frequency drive machine, variable speed machine, or a load-unload machine where we have at least 10 gallons per CFM of storage to allow it to operate on its best unloading curve. In this slide, we're looking at 2 unloading curves for a variable speed air compressors, and we notice that in the top curve, we're going to simply use the variable speed drive to ramp it all the way down to 0% capacity. However, we're going to allow the motor to continue to turn at some very nominal rotational speed at the unloaded portion when we're producing 0% capacity. So we're seeing someplace in the order of 12, 13, 14% kW or percent of rated kW at the 0% on the top curve. The bottom curve shows that when we get to 20%, if we still are producing too much air at that point, we would simply turn off the machine, and then the power would go to zero. And we can do this with a variable speed machine because that variable frequency drive has that soft starter, as we discussed a couple of slides back. And so the machine can go completely dead. And then when the pressure falls to a low point in a load-unload band, then the machine can be started back up and go to 20% load. And then if that's not enough, it can continue to ramp up and down the load-unload curve. So that's a nice option with a variable speed compressor. And so you see, if we can afford or talk management into purchasing a variable speed air compressor for our trim machine, there really are some great savings, and not only in just direct energy but also maintenance. If you're running load-unload with a machine that is loading and unloading several times a minute over the course of a number of years, that's a lot of additional wear and tear on all of the components of that system, and that's going to drive up maintenance costs in the long run. So the VFD machines are really good in terms of efficiency and minimizing maintenance cost. Here we're addressing lubricant-free rotary screw air compressors, and the bulleted items provide some characteristics and points that we want to discuss. It has the same general setup as the lubricant-injected machine. Of course, it doesn't have the sump because we're not injecting lubricant with the compressed air into the screws. The screws are typically Teflon coated to reduce friction. And the function, we can recall the function of the lubricant in the lubricant-injected machines would be that they would provide cooling, lubrication, and sealing for the rotors and the operation of the machine. So without that injected lubricant, what do we expect? Well, we expect they're going to operate at a higher temperature. They're going to be a little less efficient, and they're going to require more frequent maintenance. And all of those things are true. However, there are many applications where any lubricant, any possibility of lubricant in the compressed air is not acceptable, and so we have to go to some sort of a lubricant-free compressor. The lubricant-free rotary screw is a good option, and of course a centrifugal compressor, which we'll talk about later on in the workshop, is also a good option. Centrifugal machines tend to be larger and have some part load issues of their own that we'll discuss. The size on these machines would be typically in the 30 to 600 horsepower range, and our figure of merit, our operating cost, is on the order of 20 to 22 kW per 100 CFM, and that would be at a full load condition. At part load, that would probably go up. But if you recall, I believe we were 16 to 18, something in that range on the lubricant-injected machine. So percentage-wise, that's a significant decrease in efficiency for the lubricant-free compressors. There's a couple of pictures out there to just on the bottom picture, we can see that maybe identify the Teflon coating on the rotors, etc. And on the upper picture, it's a simpler compressor package because of the lack of lubricant being circulated all over the place, as we saw in the lubricant-injected compressors. We'll now turn our attention to centrifugal air compressors, which are fundamentally different than the reciprocating and rotary screw compressors that we have discussed to date in the workshop. This compressor is termed a dynamic machine, and what happens basically is we introduce air into an impeller spinning at a very high velocity. The air is accelerated to a high velocity itself, and then it exits the machine into a collector ring where it is slowed, and as based on the Bernoulli expression, if we take this high velocity air and slow it down, in a smooth transition, we will experience an increase in pressure. There's also an increase in temperature of the air. But as we slow that high velocity air down, the pressure increases, and that's really where the compression comes from. And so this operates more as a very high-speed fan than it does a positive displacement air compressor, which is the reciprocating, where we take a piston cylinder device, fill it up with air, and then reduce the volume, which drives up the pressure. And the rotary screw machine, which has these rotating lobes, male and female, we pull air into a gap at the top. It gets captured in that space, and as they turn, the air moves axially down the length of the screws, and its volume is reduced. So we're squeezing it, and then it spits out the outlet port. And so essentially those two machines, the reciprocating and the rotary screw, are doing the same thing, just the machines have different geometries as to their construction features. But the centrifugal compressor is more of a fan situation, and we'll typically have multiple stages, 2 or 3 stages of compression, where we'll if we're going to produce 125 psi air, we may get 40 to 50 pounds across a stage, have an intercooler where we'll cool it down again, and then go through another stage of compression, cool it down again, and then go through the final stage of compression, and then cool it down with an aftercooler before we exit the compressor package. In slide 80, we're looking at the various part load control strategies that can be implemented on centrifugal compressors. It should be noted that we can turn down the machine from 100% rated flow to 75 to 80%, depending on the manufacturer and the particular machine we're talking about, with some sort of throttling device on the inlet or inlet guide vanes at the inlet of the air compressor. The throttling would not be as efficient as the inlet guide vanes. Throttling just adds a pressure restriction on the inlet air to reduce the airflow into the compressor. The inlet guide vanes are more common. That's what you normally see in an inlet guide vane. There's a picture there of kind of just a rough depiction of inlet guide vanes, and they're kind of these pie-shaped dampers at the inlet to the air compressor that imparts a pre-rotation to the incoming air. And the more they are closed, the greater the pre-rotation and the greater the reduction in capacity of the air produced by the compressor. So what we would expect to see on most centrifugal compressors of any size would be inlet guide vane capacity control from 100%. At 100%, the inlet guide vanes would just be completely open, down to about 75 to 80%, in which case the inlet guide vanes would be closed as much as they could be. If we need less air than, say, 75 to 80%, then typically what happens is there is a blow-off valve, and that additional air that the system doesn't need is blown through the roof, which is not efficient at all. And so a lot of efficiency efforts related to centrifugal compressors revolve around trying to minimize or eliminate the operation of the blow-off valve. And the problem is that, say you have, in centrifugal machines tend to be large ones, and they like to be base loaded, or to have just very, not large capacity modulation range on them. So let's say if you had a machine that was sized for 10,000 standard cubic feet per minute, and you can operate that machine efficiently and effectively between 8,000 and 10,000. But let's say your system demand drops off significantly and you only need 4,000. Well, so how can you get there? If you put more than 4,000 into your system, you're going to drive your pressure up and lose pressure control. And you can't do that with a compressed air system. So if the demand on that machine is 4,000, we can turn down from 10,000 to 8,000 or so with the inlet guide vanes, and we can do that efficiently. And then from 8,000 to 4,000, we're going to have to take that amount of air and blow it through the roof. So you can see that's not going to be very efficient at all. So centrifugals don't make very good trim machines, but they make excellent baseload machines, and they do provide lubricant-free air. It is possible, if you have enough storage, that you can run these load-unload. So in the scenario that I just discussed, once you reach the 8,000 CFM demand point, you wanted to go down from there. If the machine was set up with load-unload controls, then the machine could unload, just like the previous curves we've seen, and then achieve the 4,000 CFM very efficiently. The problem is most systems utilizing centrifugal air compressors don't have significant storage, and so they can't be operated in the load-unload mode fashion. They would load and unload much too rapidly, and that would damage the machine. The rule of thumb is at least 7 gallons per CFM on the trim machine. And so if that 10,000 CFM machine was going to be your trim machine in the example, that would require 70,000 gallons of storage on site close to the compressors, and most systems just don't have that much. On this slide, we continue to explore the capacity modulation options for centrifugal compressors that we talked through in a fair amount of detail on the previous slide, but this is a graphical depiction of most of our options, and we see on this slide that we can go from 100% capacity. This slide shows about going down to 70% with inlet guide vanes. Again, it depends on the manufacturer and the particular compressor, what that minimum point is. But if you were to try to go below that minimum point of, again, about 70% on this slide with the inlet guide vanes, we would quickly encounter a surge condition on the compressor, and that's where we would lose the aerodynamics of the flow through the impeller, and the machine becomes unstable, and it's with vibrations, etc., and you cannot operate there. The manufacturers are very careful to set up their control systems to not allow operation in a surge condition on a centrifugal compressor. So if all we have are inlet guide vanes and a blow-off valve, then you see at, say, 50% rated capacity, the blow-off valve is well in operation, and so the difference in capacity between what we need, say 70% air, and the 50% is blown through the roof. There's simply, if you look on a compressor package, you can either see a readout on the controls, or sometimes you can actually see the blow-off valve itself and look and read off the valve what its position is. But for efficient operation, we want those blow-off valves shut. We don't want to spend the money to make good compressed air and just vent it through the roof. And so with inlet guide vanes and blow-off valve control, we can never get below 75% rated power on the machine, even if we're producing no air. If we're producing no air, then it's simply all blowing out the roof. And of course, that brings up a lot of other issues. For example, if we did a compressed air leak reduction program in a large facility, but the air compressors were operating in blow-off, then if we reduce the amount of air that the system is going to require, do we save any money? And the answer is absolutely not. We simply reposition the blow-off valve, and instead of blowing it out the leaks out in the plant and around the manufacturing equipment, we simply blow it up the roof at the location of the compressor with no savings whatsoever. So we have to be careful just because we go out and reduce compressed air usage or leaks. If we don't change something back at the compressor to reduce the compressor's energy use, then there's no energy savings. And we also see the load-unload line here, which is really nice. And there are some. I have seen large centrifugal compressors that operating on master controllers that would unload, and even if they're unloaded long enough, it's possible to shut off the motors if you have enough compressors so that you can rotate around and not get too many starts and stops on a particular motor. It's possible to utilize variable frequency drives on centrifugal air compressors, but in a practical sense, you don't see many of those out in the field. Here we're illustrating some additional features related to the operation of a centrifugal air compressor. This is what we would call a compressor curve for a particular compressor. And we see several features of interest. This machine has been set up to produce 125 pounds per square inch gauge compressed air. And we see the horizontal line that would intersect the pressure axis at the 125. Where that horizontal line intersects the surge line, that would represent the minimum SCFM of air that compressor could produce without going into surge. So if that compressor was required to only produce 500 SCFM to maintain the pressure in the system, then the difference between, say, the 900, or I guess maybe that's 890, and the 500 would have to be vented through the blow-off valve. Or if the compressor was set up to run load-unload, then the machine could unload for a portion of the time to account for the reduced needed capacity from that compressor. A couple other features: the temperature of the inlet air to the centrifugal compressor actually has an impact on its maximum capacity. We see that we have the curved line that intersects the 125 PSIG compressor line at about 1390 SCFM. And so if we have, on a hot summer day, if we're bringing 95-degree air into that air compressor, about 1390 SCFM is going to be its maximum capacity. And there is a particular power associated with that. If, however, on a fall or winter day, we're bringing 55-degree air into that compressor, then we would see that the capacity would increase to about 1580 standard cubic feet. So the colder the inlet air to the centrifugal compressor, the more capacity you get out of the machine. And that can be a good thing. The other thing that you have to realize, though, is that as we put colder air into the compressor, it's going to require more power in order to operate the compressor. And if you put in colder air than the machine was selected for, you can overload the motor. That can lead to downtime either on high temperature, or it would be possible if your thermal protection on the motor did not work, possibly that you could burn up a motor. In slide 83, we're looking at some additional characteristics of centrifugal air compressors. Here we see, again, the surge line, and we see that as the pressure is reset on the machine, we change the minimum amount of airflow that the machine can produce. At, say, 60 pounds pressure set point, we can go down to 50% flow. As high at the 100 pound pressure set point, we're at about 80%. And so that's simply a characteristics where we encounter the surge line on the machine. Again, the manufacturer is not going to let you operate in a surge condition. He will shut down the machine or open a blow-off valve or take some action to protect the equipment. And then on the red curve on the right-hand side shows the aerodynamic limit. At each pressure set point, there is a maximum airflow that the compressor can produce. And we see as we drop pressure on the machine, we can actually get additional compressed air out of it. So that's additional motivation in an efficiency study to determine what is the lowest possible air pressure that we can operate the system at, and drop it to that. With a centrifugal compressor, you may actually save some money by unloading this compressor, or you may, if this is a base-loaded compressor, we drop system pressure, we might have a variable speed machine that then can throttle back its air production and reduce the overall operating cost of the system. I will note again, however, if we drop pressure and we only have centrifugal compressors in the system and they're operating, at least one of them is operating with a blow-off valve open, we drop pressure, each compressor will make more air, we will simply reposition the blow-off valve and not save any energy perhaps at all. Here we're looking at some crude photos of impellers designed to operate with centrifugal air compressors. And we see these things are generally not terribly large. They may be 5, 6, 7 inches diameter at the widest point. They are designed to operate at extremely high rotational speeds, someplace between 30 and 60,000 revolutions per second, tremendously high rotational speeds. And we see at the bottom portion of the figure that we see two stages, two impellers on the same shaft, where the air would go through one. We would achieve partial compression, and it's typical then that air would be cooled in an intercooler. That will reduce the energy requirement by the machine to keep the air as cool as possible as it goes through the various stages. So we typically will have intercoolers with a water flow rate from, say, a cooling tower system to cool the air. We also condense out a bunch of moisture at each intercooler and the aftercooler. And then so we would go through the first stage of compression, go through an intercooler, cool it back down, go through a second stage of compression, and if there was just two, then it would go to the aftercooler and on out to the system. So you can see kind of a crude flow diagram for single and two-stage compressors. Slide 85 is our summary slide on centrifugal air compressors. We see the first bulleted item just reflects the general operating characteristic that the high-speed impeller will impart a high degree of kinetic energy to the air flowing through it. Then the air flows into a diffuser which slows it down, converting a lot of that velocity energy to pressure. We typically have multi-stage centrifugal compressors, 2 or 3 stages of compression, 2 or 3 impellers. They're usually larger machines. 200, it would be a small centrifugal. We often see 1,000 horsepower to 2,000 horsepower machines. An important characteristic is that we get lubricant-free compressed air from a centrifugal, which is very important in a lot of applications. And they are relatively efficient machines, 16 to 20 kW per 100 CFM at the fully loaded condition. I have even seen machines that were slightly more efficient than this. So long as we can operate them at pretty close to full load, they are very efficient. They make great baseload air compressors. Pictured in this slide are the drain lines coming from 2 intercoolers and the aftercooler on a 1,500 horsepower centrifugal air compressor. We can see that there are no condensate traps to reduce the air loss on draining the moisture from these heat exchangers. And we have 3/4 inch lines, or I take it back, I think those are 1/2 inch lines, but we have significant lines with simply a valve that is some degree open. We're not really sure. I guess we can look at the stems. The stems look pretty much elevated on those, so the assumption would be that those are pretty much wide open valves to allow the moisture to drain from the intercoolers and the aftercooler, which is of course required. We cannot allow that condensation to back up into the machine and get into the rotors, or it will absolutely destroy those rotors, and it would be a catastrophic failure of the machine. So to vent and drain the moisture is required. However, we can put a zero loss compressed air trap, which is there is a photograph of one on the lower portion of the slide that can completely eliminate the air loss. Some measurements and estimations were made on the amount of airflow coming out of those three vents, and I can tell you it was deafening. Without hearing protection, you could not stand close to those drain lines. It was just too loud. And the estimate is that those three lines were venting roughly 20% of the compressed air that was generated by that 1,500 horsepower compressor. So it's a significant issue. You see on centrifugals especially, you see this sometimes. And of course the problem is that if the drain traps fail, you can wreck the compressor. But on the other side of things, it's extremely inefficient to vent that much compressed air directly at the compressor location. Another option is to, when the traps are installed, you can install two traps in parallel on each vent line. That way, if either one of those traps was to fail in a closed position, the remaining trap could still handle the condensate flow and would avoid backing up into that moisture into the compressor, causing the major failure. And then by checking those traps on a daily or weekly basis, one would hope that you could eliminate the possibility of having both traps fail on one line at the same time. On this slide, we're comparing the relative efficiencies of the different types of air compressors that we have discussed in the workshop. And so obviously the lower the kW per 100 CFM produced by the compressor, the more efficient the machine. We see that the double-acting two-stage reciprocating compressor in the 15 to 16 kW per 100 CFM range is probably the most efficient. The centrifugal machines are quite good when they are base loaded or almost fully loaded. I have seen them as low as 15 on calculations, but the typical rating is 16 to 20. And we see then the lubricant injected rotary screw machines, a two-stage might be 16 to 17, single stage 18 to 19, and the lubricant-free machines, depending on number of stages, 18 to 22. The single-acting reciprocating, those are the smaller shop-type compressors, are not terribly efficient. Slide 88, we show the picture of a pressure flow controller. This is a device that can be installed in your compressed air system that can limit the fluctuation in the downstream air pressure to roughly plus or minus a half to 1 psi. Some applications require that the supply air pressure for the compressed air be very constant over the entire operating time for the system. And this is a device that can accomplish that for you. Well, this will be discussed in greater detail on the next slide. The basic operation of a pressure flow controller requires a significant amount of upstream storage at a pressure probably 5 to 10 psi above the pressure that you want to maintain downstream of the pressure flow controller, which would be the pressure that your system would see. Again, these pressure flow controllers can hold that downstream pressure plus or minus a half to 1 psi, so long as they have enough air stored back upstream. So they help to minimize artificial demand. That artificial demand would be if we have significant variations in the compressed air pressure, i.e. if we're operating load-unload control, we're going to have typically at least a 5 and more likely a 10 psi band, so that we would then drive the pressure up 10 psi above the minimum just to facilitate the part load capacity control on the compressor. So that during the portions of the day when the pressure is above that minimum, then any leaks or open blowing applications would pass more air than they would otherwise. That's what we mean by artificial demand. They obviously must be engineered properly to work with each particular systems. They do require that you raise your compressor pressure 5 to 10 psi higher than the desired system pressure. This slide will illustrate the importance of the part load capacity control strategy employed on the compressor. So we are assuming here that we've had a compressed air leak survey done, and we've eliminated enough leak flow that would reduce our 10% of our compressed air demand. Ideally, the savings, we'd like to think that we're going to save 10% of the cost of generating the compressed air if we reduce the flow rate by 10%. However, the chances of that are pretty slim. And, we have to always keep in mind that we can reduce leaks, we can reduce compressed air usage. That's fine out in the plant or in the process. But we have to save the energy at the compressor. And if the compressor does not unload or use less energy, then we're not going to save anything. Now, that's not to say that there may not be a good reason to fix compressed air leaks anyway, but it would be naive to think that a 10% reduction in compressed air generation or compressed air usage based on leak reduction was actually going to save 10% of the operating cost. So that's what we're going to illustrate in the next couple of slides. The efficiency of the compressor control system will tell the tale of the energy savings. And again, the last bullet here, this refers back to the centrifugal compressor. And again, we mentioned this previously, but if the blow-off valve is already open and we fix a bunch of leaks, all we're going to do is reposition it, and the compressor will use no less energy than it did before. Okay, so we have accomplished a 10% reduction in compressed air demand. Let's look and see how we can turn that into estimated dollar savings based on the part load operation of the air compressors. So in this slide, we show the unloading curve for the rotary screw air compressor under modulation or suction throttling type control. And if before our 10% reduction, the compressor was operating at typically 60% required airflow, then we go up to the curve and over to the power axis, and we see that that compressor was typically consuming 90% of full load power. So now we'll have to take our 10% reduction into consideration on the following slides. Moving forward with our example of a 10% reduction in compressed air usage based on a leak reduction program, we have here an unloading curve for a rotary screw air compressor that would be using modulation control, that butterfly valve at the suction, also known as suction throttling. And we see, for example, previously before the leak reduction, we were operating at 60% required compressor capacity, and that 10% reduction would drop us to 50%. And so, but to see what's going to happen at the compressor, we have to go up to the compressor control curves. And so what we see is that at 60% air production, the compressor power was 90% of full load with modulation. And when we dropped the air usage to 50%, that translates up to the modulation curve and over to 87.5% full load power, which means that we only save 2.5% of the full load energy input to the compressor as a result of the 10% reduction in required air production. Moving forward with our 10% reduction in compressed air demand, now we see a compressor curve for ideal load-unload control. And when we look at our 60% required flow before the leak reduction program, we see that that would have translated into 72% of the full load capacity, or the full load power requirement of the compressor, I should say. And at 50%, then the power requirement is going to drop to 64% full load power. And so that's going to save us 8% of the full load input power on the air compressor as a result of the leak reduction program. Finishing up our compressed air demand reduction exercise, we put the results for both types of compressor control on the same slide just to illustrate. And so we see here that we may well reduce the demand or usage of compressed air, but the amount of reduction in operating cost goes back to the part load efficiency of the compressor that actually backs off. So again, if we were using modulation or suction control, that 10% reduction would yield us only 2.5% of full load power. However, if we were using load-unload with an ideal curve, i.e. we had a lot of storage, then we could yield an 8% energy savings. In slide 94, we have a different comparison. We're going to start out with 3 equal air compressors that are being operated simultaneously, and they're all being operated at 60% full load flow or capacity. And we see they're going to be operating at 75% input power because they're on a fairly ideal load-unload curve. Okay, so if we look at the total operation of the system, we're going to see that the flow requirement or the compressed air requirement is 180% of the air that can be produced by one compressor, and the total power requirement, or the power being consumed, is 225% of the full load power of one compressor. Now, is there a more efficient way to operate this? I think so, and that will be illustrated on the next slide. The modification to the compressor operation has been to shut down one machine, to operate the second machine at 100% capacity, and to operate the second machine at 80% capacity, so we still get our 180% of one compressor capacity, and now we're only utilizing 190% of the input power to one full load compressor, i.e. we have saved 35% of the full load energy input to one compressor, and by having one machine offline. Now, there could be reliability concerns based on this. Some companies will decide that, well, we would rather operate a third machine in case one machine was to go down unexpectedly. We would have 2 machines that could still maintain system pressure. So there are other issues that need to be worked through before you necessarily go down to 2 machine operations, because if you're operating 2 and you lose one, you're going to most likely lose your system air pressure for at least a little while until the second machine is started. That's if you're operating things manually. If you're operating things with a master controller, it's certainly possible to catch any sort of a failure and start an additional compressor in time to preserve your system pressure. But the master controller could represent a $20,000 to $40,000 expense. And not a lot of people have those. Some do, some don't. So that would be a consideration.
The next section of the course will be on compressed air conditioning, and the Major components of it will be a discussion on moisture removal. We'll look at two types of compressed air dryers: the refrigerated air dryer, which produces a dew point temperature of 35 to 38 degrees, and then desiccant type dryers, which can produce dew point temperatures between minus 40 and all the way down to, say, minus 200 degrees Fahrenheit. In general, the cost of conditioning the compressed air increases with the quality of the air, i.e. if we have drier air, it's going to cost more to run that dryer than it would if we can accept a higher dew point. The general rule of thumb is we need to keep the dew point temperature of the air inside the piping a good 15 to 18 degrees above the lowest ambient temperature that piping will see. And so if the piping is all inside the plant and the plant is heated to any significant extent, then the refrigerated air dryer will probably be sufficient. If the piping goes outside and is exposed to cold winter temperatures, that may lead us into a desiccant dryer, which will up the operating cost. We'll also speak some on different types of filtration that can be used with compressed air. We have particulate filters, we have coalescing filters for liquid, and we have absorptive type filters for vapors.
Compressed air needs to be dried to a dew point that is well below that of the temperatures that will be experienced in the compressed air distribution system. So the DOE Compressed Air Challenge recommends that the compressed air be dried to a dew point that's at least 18 degrees F below the lowest ambient temperature to which the system is exposed. Sometimes that's not completely possible, but the plan would be to get the dew point of the air significantly below the coldest temperature. So, if all of the compressed air lines run inside and a plant is heated to some degree, we might assume that 45 or 50 degrees might be the coldest temperature to which the distribution system would see. So if it was 45, we came down 10, that would be 35 on dew point. You can accomplish that with a refrigerated air dryer, as we'll see. If you consider the lowest temperature the distribution system would see to be 55, 45, 35, then you could easily be within the DOE Compressed Air Challenge recommendation. So, however, if the lines run outside and you're in any sort of a cold climate, you're going to have issues on a day. It could be 0 or 5, 10 degrees outside. Then refrigerated air dryer is not going to remove enough moisture from the compressed air, and if you don't go to a desiccant, then you're going to be looking at the potential for condensation and freeze up in your outside piping. Liquid water inside compressed air systems can cause a variety of problems, which are illustrated here. Certainly, as we mentioned previously, if the piping runs outside and we get condensation, that can obviously freeze and can clog up and prevent airflow or drastically restrict the amount of compressed air that can flow through the distribution lines. Wet pipes on the inside of the distribution system will cause corrosion, and if this gets enough out of hand, we start to exfoliate some of the corrosion products, some of the rust on the inside of the pipe, and then that can travel with the compressed air to small orifices and passages in different types of control equipment. It can clog those up and cause them to malfunction. And just certain types of equipment that receive compressed air cannot tolerate liquid water being supplied to them with the compressed airflow, and they will just shut down. And so I have seen entire process lines and buildings shut down based on too much moisture in the compressed air system. The source of the moisture is from the outside ambient air, which is drawn into the compressor, and then it just passes through the compressor and exits. If it doesn't get condensed out, then that water vapor will be in the air. There's a certain dew point, and if the lines of the system fall to or below that dew point, we have liquid water condense out inside the compressed air system. As an example, on a warm summer day, we might have 95 degrees Fahrenheit outside dry bulb, 75% relative humidity. A 200 horsepower air compressor is going to be delivering somewhere on the order of 950 standard cubic feet per minute. It's going to pull in over 105.4 pounds mass per hour of water vapor, and if condensed, that would equate to 12.7 gallons per hour. So we really have to manage this moisture issue with our compressed air systems. Let's track the water vapor as it moves through the compressor and the aftercooler and the dryer to see the relative amounts of water that are being handled, the dew points, etc. Okay, so for air at 95 degrees F, 75% relative humidity, at 14.7 psia atmospheric pressure, we look the vapor pressure for the water vapor will be, its partial pressure will be 0.6122 pounds per square inch absolute. So if we take 14.7 minus that, we get the rest of the partial pressure would be for the dry air, which would be 14.0878 psia. And the dew point just in the ambient air outside is 85.8 degrees Fahrenheit. Okay, so we run that through our air compressor, which increases the total pressure to 100 psig, or 114.7 psia. We'll see that the vapor pressure has been increased of the water vapor to 4.7768 psia, and the pressure of the dry air then is the difference between that and 114.7, and that's 109.9232 psia, and the dew point at that point exiting the compressor is 160.3. So we're going to definitely be condensing some water. Okay, so then the air flows through the aftercooler, which is part of the compressor package, and we typically cool it down to 100 degrees Fahrenheit, and so the air would leave at 100 degrees Fahrenheit at saturation, or with a relative humidity of 100%. If we look at the amount of moisture removal by the aftercooler, we see it's 10.28 gallons per hour. That's a bunch of water. Okay. Then we move on to the refrigerated air dryer that's in the system, and it has a refrigeration process internal to it, and as the air is treated, it will be cooled to 38 degrees inside the air dryer, and that will remove an additional 2.16 gallons per hour of water. Okay, and so when the compressed air leaves the dryer, it is cooled to that temperature and then reheated with the incoming air stream and a counterflow heat exchanger, so it boosted up to 65, 60, 70 degrees, something like that, before we put it out into the piping. But it still leaves 0.29 gallons per hour of water vapor in the compressed air stream that is sitting there at a dew point of 38 degrees that can condense out. So if that air encounters 38 degrees or colder in the piping system, then we'll have liquid water to deal with. This slide just shows a standard atmospheric pressure psychometric chart that can be used to help you determine the amount of moisture in your outside air going into the system. Once the pressure is increased, then this chart can no longer be used. This is good for sea level atmospheric pressure, which is roughly 14.7 pounds per square inch absolute. The aftercooler is a critical component for the proper operation of the compressed air system. The aftercooler takes air from the compression element. On a rotary screw compressor, it would receive the air directly from the screws. On a reciprocating compressor, as the air exits the piston cylinders, it would go to the aftercooler, and the aftercooler will cool the air to a maximum of 100 degrees Fahrenheit. And if the cooling media, either typically air or water, is colder than its design spec, the air leaving the aftercooler may well be cooler than 100. But that is a critical temperature to check for the proper operation of your system would be that the compressed air leaving your compressor package was 100 degrees F or cooler on its route to filters and the dryer for additional moisture removal. Typically, 70-80% of the total moisture entering the air compressor with the compressed air is removed by the aftercooler. And so you can see that we have to have proper functioning of the aftercooler. If we don't, the moisture load to the dryer will simply overwhelm it, because the dryer is never intended to take the place of the aftercooler. We usually see a moisture separator and automatically controlled drains to collect and remove condensate, i.e. liquid water, from the compressed air stream after it is condensed out by the aftercooler. And these have to be sized to handle a significant moisture load. Aftercoolers are rated by either a temperature differential across it or an approach temperature, which would be a number indicating how closely they can cool the rated airflow to the incoming temperature of the cooling medium. That would be, again, typically air or water. We wish to reiterate here that the performance of the aftercooler and the moisture separator should be monitored to assure that your system is going to perform correctly and reliably. A properly applied aftercooler and separator will have a negligible, very small pressure loss. So you should be able to measure the actual pressure loss and make sure that it is not creeping up due to some sort of a fouling issue. There are different types of moisture separators that we see. Some are centrifugal in nature. We also have wire mesh mechanical coalescing separators. And thirdly, we have mechanical impingement separators. The first type of compressed air dryer that we will investigate in the workshop will be the refrigerant type dryer. These dryers are typically rated for 100 psi inlet compressed air pressure from the compressor package, supplied at 100 degrees Fahrenheit, and the dryer can sit in an ambient location where the temperature is up to 100 degrees Fahrenheit. If we exceed any of these three numbers, 100 psi, 100 degrees F ambient, or 100 degrees F inlet air temperature, we will derate the capacity of the dryer. So if that is expected, then that needs to be taken into consideration when the dryer is selected. Internally, refrigerant type dryer has a refrigeration system, as the name would indicate, and the air is cooled to a temperature between 35 and 38 degrees, which condenses out the moisture. So the relative humidity leaving that coil internal to the dryer would be 100% at 35 to 38 degrees Fahrenheit, and that would set the dew point on the air leaving the dryer. Refrigerant type dryers are good for many, perhaps even most industrial plants and automotive applications. Typically, the key element to look for is, does the compressed air distribution system have lines that go outside that will be exposed to winter temperatures that are in the mid-30s or colder? If the answer to that is yes, then perhaps the refrigerant dryer is not the correct choice for you. If the answer is no, and all of the compressed air distribution system is inside a heated or at least somewhat heated area, the refrigerant type dryer will most likely work for you. We have to be sure and keep the after coolers on the compressor package and the dryer condenser clean. This is a heat exchanger and the refrigeration system of the dryer that rejects heat to the ambient. And we will typically have to pre-filter and post-filter or after-filter the compressed air into and out of the refrigerant dryer. We want to be able to be sure to pick up any moisture, any droplets. So we would need coalescing type filters. And on the inlet, it's a good idea to have a particulate filter to pick up any particulate matter that might be exiting the air compressor. Slide 105 shows a schematic diagram of a refrigerant type dryer. We notice that on the left-hand side we have wet air inlet. That's the basically saturated air coming over from the air compressor at about 100 degrees, maybe a little bit cooler. And the first component inside the dryer package would be an air-to-air heat exchanger. And so what we're going to do in this heat exchanger, we're going to take air that has already been cooled and dried by the refrigeration process inside the dryer, which would be very cold, probably 35 to 38 degrees, and we're going to warm it up with the warm, wet inlet air coming out of the compressor package. This accomplishes two purposes. First of all, we don't want to put 35 to 38 degree air out in a piping system in the plant. That's going to be below the dew point of the air on the outside of the distribution pipes, and they're going to sweat like crazy. So you're going to have puddles of condensate falling off all over the place onto the floor or whatever they happen to hit if we don't heat that the air up after it goes through the refrigeration portion of the drying cycle. So we're going to warm it up, and we likewise will cool down the wet inlet air, and that will help the dryer by supplying the refrigeration circuit with cooler air than would otherwise. So this diagram shows a separator and trap on the wet inlet air side after it goes through the heat exchanger, because there will be moisture condensed in that cooling process. The air then goes on to the refrigerant coil where it is cooled down to the low temperature, the 35 to 38. Then we're showing another separator and trap with additional liquid water removal. And then that cold air exits and goes through the air-to-air heat exchanger before exiting as dry, relatively warm compressed air, probably up in the 60s, something like that, high 50s to 60s. Here we're looking at the first half of the cycle of a thermal mass refrigerant type dryer. So we see the refrigeration circuit with the compressor that's putting out superheated refrigerant vapor to a condenser coil that has a fan that's blowing ambient air across it. That refrigerant's pretty warm, 150, 160s typically, is cooled down and condensed at high pressure. It then goes through a filter dryer just on the refrigerant line, and it goes through the thermal expansion device. And then the thermal expansion device drops pressure, which then reduces the temperature to in the range of 33, 34 degrees. And then that cold refrigerant goes through a heat exchanger in a tank that is filled with a cold propylene glycol water mixture. That is the thermal mass. And so then the refrigerant, some of it, it boils off into the vapor state and returns to the compressor. So that would be the refrigerant loop. And that tank, the glycol tank, is maintained at the 35 to 38 degrees, and that is really the thermal mass that smooths out the operation of the dryer. In this slide, we see a continuation of the thermal mass refrigerant type dryer. Down at the bottom of this slide on the lower left, we see a line coming from the cold glycol supply tank, or the thermal mass tank, a small pump that is pumping that cold glycol through the one side of the air chiller that supplies the cold glycol flow that actually does the cooling of the compressed air. On the other side, we see that we have another stainless steel pre-cooler reheater heat exchanger. That's an air-to-air heat exchanger. On the red line, we see the moist air coming in from the air compressor. It goes through that heat exchanger where it is pre-cooled with the exiting compressed air that has already gone through the air chiller coil. That cools it down some and does condense out some moisture. And then it goes through the air chiller coil where it is cooled to very close to the glycol temperature, the 35, 38 degrees. It then exits that side of the coil down at the bottom right and goes to the centrifugal air moisture separator, where we eliminate all of the liquid, the droplets, and the liquid water that has been condensed out in that air chiller coil. And then that cold air goes to the stainless steel pre-cooler reheater coil and pre-cools the incoming air directly from the compressor package. And then the dry air is heated up and it exits to the compressed air system. We're looking at some manufacturers' information on refrigerated air dryers made by one of the major compressed air manufacturers in the country. This just shows for a particular model of dryer that we have units available as small as 200 SCFM all the way up to 8,000 standard cubic feet per minute. And the dryer leaving spec would be for a 38 degree dew point. The pressure drop across the unit is given in the third column. It's typically for the smallest unit is 1.6 pounds per square inch, and the larger units are rated at 3 pounds per square inch. We have operating kW, how much power is it going to take to operate these dryers, and notice we have a column for air-cooled and water-cooled. And so we see that water-cooled dryers are more efficient, i.e. they require less input power. That's because water is a more effective cooling medium than air, and it would typically come to the unit colder than the ambient air would, at least in the summertime. So we can see, say on the largest dryer, the air-cooled unit is about 43.5 kW of input power, and the water-cooled unit is about 30.5. So significant difference in required power to operate the dryer based on the cooling medium selected. So if a cooling tower loop is available, then it would obviously be a better option. Then we also see the dimensions. We see the approximate shipping weight and the type of air in and out connections to the dryer that come from the manufacturer. As we mentioned previously, refrigerator dryers are typically sized for 100 degree PSIG inlet compressed air at 100 degrees Fahrenheit, with the dryer sitting in an ambient location that is 100 degrees Fahrenheit. If any of these three 100s, as far as a selection design situation, are different from that, then we need to apply correction factors so that the appropriate model of dryer with the appropriate capacity is selected. We see a sample calculation here. Dryer selection example 500 SCFM would be the designed airflow rate from the compressor at 110 degrees inlet temperature. The inlet compressed air pressure is 125, and the compressor is expected to be sitting in an ambient at 100 degrees F or cooler. And so as you look across that chart from the left-hand side, the 110 degree inlet leads to a correction factor of 0.81. The 125 PSIG inlet pressure leads to a correction factor of 1.08, and the 100 degrees ambient leads to a correction factor of 1, which is basically no correction at all. Then down at the bottom of the slide, we see the dryer size calculation. We take the 500 SCFM of inlet compressed air from the compressor, and we divide that by the product of all three of those factors, the 0.81 times 1.08 times 1, and that the result of that calculation is 572 SCFM would be the dryer capacity that we need as far as sizing the dryer, and that would lead us to a 600 SCFM dryer, even though the inlet airflow is only 500 SCFM. We are now moving on to regenerative desiccant type dryers. And again, from a selection point of view, they are typically rated for 100 PSIG inlet air at 100 degrees F from the aftercooler of the compressor package and 100% relative humidity. We need to pay close attention to the inlet temperature. It's critical in the proper operation of the dryer. These dryers use a porous desiccant that absorbs moisture. Basically, the moisture, the water vapor molecules stick in little crevices and cracks in the fairly porous desiccant. Once it becomes saturated, it then has to be regenerated so that it can be reused. We can get extremely low dew points from desiccant dryers. The standard number you usually see is minus 40 degrees F on a dew point, but they can be sized for down to minus 100 degrees F. That would be for a specialty application such as perhaps a pharmaceutical operation or manufacturer. But the standard on the desiccant dryers is minus 40, and it's very unlikely that we're going to see temperatures approaching minus 40 any place in the United States. I guess maybe sometime in Alaska you might see that, but typically minus 40 is dry enough to keep the water in the vapor state. Generally, air that's dried to this extent would be used for, again, specialty processes, instrument air, or outdoor applications. If we have an extensive compressed air distribution system that is going between buildings and we're going to see cold winter temperatures, then perhaps a desiccant dryers would be required to keep moisture from condensing in those outside compressed air lines during cold winter weather. It's always good to keep in mind we could consider small regenerative type desiccant dryers just at a point of application, whereas the entire compressed air system would not need to be dried to a dew point of -40, but we might have just certain particular applications that required that. The operation of a desiccant dryer is significantly more expensive than that of a refrigerant air dryer, and so we would not want to use desiccant dryers on every bit of compressed air generated unless we absolutely had to. Pre-filtration and post-filtration is required. The post-filtration here is because the desiccant will give off small particles, or called fines, of the desiccant material that can get out into the piping system, and that needs to be filtered right at the exit of the desiccant dryer. Here we're looking at a schematic diagram of a heatless or a regenerative desiccant dryer that does not heat the regeneration air. So we see an air compressor element that then delivers its compressed air, hot, moist compressed air, into the aftercooler. The aftercooler then cools it to nominally 100 degrees, and removing that 70-80% of the total moisture load. We then see a moisture separator and a trap to get all of that liquid water out of the system. And then we move into the desiccant dryer itself. We see twin drying towers. That's a standard configuration. One tower will actually be drying the compressed air, while the other tower is regenerating, or having the moisture driven out of that tank so that it will then be ready when the current drying tank is saturated, and they switch back and forth on some sort of a design time interval. So we see all of the air is dried by the drying tower. It comes out into the supply air line, and then the regenerating tower taps off approximately 15% of the rated capacity of the dryer and takes that air and vents it through the regenerating tower to atmosphere. And that carries away the moisture that was captured out of the compressed air when the regenerating tower was in the drying mode. For example, if this dryer is rated for 1,000 SCFM, 150 SCFM of dry, compressed air that's ready to go out to the system is tapped off and used to regenerate the offline tower. And so that's where the expense comes from. It's like a huge leak in your system. So if your system was sized for 1,000 SCFM, you've got a 15% leak off of the top, which is caused by the operation of your regenerative desiccant dryer. A second type of regenerative desiccant dryer would be the exhaust purge unit. And the modification here from the previous desiccant dryer that we looked at in the previous slide is the addition of a heating element to heat up the regeneration airflow of compressed air before it goes through the regenerating tower. And so we see that the addition of the heater drops the required regenerating airflow from 15% to 7%, which of course would potentially improve the efficiency and the cost of operating the dryer. Now, the other issue that would have to be investigated is, what is the heating source? What is the energy to drive the heater on the regeneration airflow? If that's electricity, then that's a fairly expensive energy source, and we would have to look at it. It will reduce the operating cost from the 15% regenerative dryer down to the 7%, even if it is electricity, but the savings are not as great. If that could be waste heat from some sort of a waste heat source, then after we had purchased the heat exchangers to accomplish the heating, we would have no ongoing operating costs to heat that regeneration airstream. So other than the heater, it's exactly the same as the previous slide. The addition of the heater again reduces the amount of good compressed air we must vent to regenerate the desiccant from 15% to 7%. The third type of desiccant dryer investigated is the blower purge unit. And the modification here is that instead of using dried compressed air to regenerate the offline tower, we are going to use ambient air. We're going to provide a fairly low pressure blower and a heating element on the discharge of the blower to get sufficient temperature to regenerate the desiccant. And then that air is blown to atmosphere and along with the moisture that had been captured in the drying tower. So this will again reduce the operating cost on the dryer. We do have to put energy into the blower, but we're not going to increase the pressure on that ambient air going through the blower anywhere close to the pressure that is generated by the air compressor. That might be 10, 15, 20 psi G coming out of the blower, as opposed to the air compressor, which is probably going to be pumping up between 90 and 120 pounds per square inch. So this is a good modification to the desiccant dryer. It will up the first cost on the dryer because we have to purchase an additional blower, controls, heating element, etc. The long-term cost of ownership of that dryer would definitely be lower than the other two desiccant dryers investigated. The fourth and final type of regenerative desiccant dryer discussed in the workshop would be the heat of compression dryer. And this is a little bit of a specialty application for the integration of the desiccant dryer with the compressor package. So what we're showing here is we take all of the discharge air from the air compressor before the aftercooler. Of course, so this air is going to be extremely moist, and the requirement for the operation of this dryer is that temperature must be above 250 degrees. So then that air would go directly into the desiccant tower that needed to be regenerated, that was offline because it had become saturated. And we have to blow the moisture out of that tower. And so we're going to use this very moist but very hot compressed air directly from the compression element. So then that even moister air exits the regenerating tower and goes to the aftercooler, which then will remove a significant amount of moisture. The air then goes to the separator and trap to get all that liquid water out of the system. We then go to the drying tower, which would then remove virtually all of the remaining moisture. I mean, you can't get all of it, but it would be extremely dry when it comes out of the drying tower on the desiccant. So we would expect a minus 40 nominally dew point coming out of the drying tower that then would be supplied out to the system. So in order to make this heat of compression dryer work, it has to be integrated into the compressor package so that we can flow through the regenerating tower before we go to the aftercooler. And that's not the standard compressor package that the manufacturers will put out. So if you want this type of a dryer, it has to be integrated in with the operation of the air compressor. Here we have a couple of photographs of two different desiccant dryers. The general characteristics, please note that we have the two large tanks, each of which contain desiccant material. And of course the controls switch back and forth so that one cylinder is drying compressed air while the other cylinder is being regenerated. The dryer on the left does not have any sort of heating capability, and so it's going to vent roughly 15% of the dryer rated capacity through the regenerating cylinder pretty much all of the time. They do, some compressor packages do have some more intelligent controls that can monitor the moisture content or dew point of the air coming out of the regenerating tower and throttle back the amount of compressed air once that tower becomes dry. The older or less intelligent control systems will simply vent 15% of the rated dryer capacity at all times. The dryer on the right-hand side is a heated purge desiccant dryer, and so you see the kind of larger control box in between the two desiccant cylinders or towers, and that in this case includes electric resistance heating elements to heat up the purge air, compressed air, before it goes through the regenerating tower, which drops that flow rate from the 15% down to 7% of the rated capacity of the dryer. In this slide, we're looking at a relative comparison of the cost of operating different types of compressed air dryers over the course of a year. We're looking at drying 1,000 standard cubic feet per minute for 1 year. We see the different dew points that are available from the different technologies. The first two, the deliquescent and the standard refrigerated air dryer, you just don't see those very much anymore, so they've not been really included in this discussion. The heat recovery refrigerant dryer will cost about $3,500 per year per 1,000 SCFM, and is going to get us a dew point of 35 to 38 degrees. Then we go into the four of the desiccant dryers, and we see the heatless that is venting 15% of the capacity of that dryer. So in this case, if it's 1,000 SCFM dryer, it's going to be venting 150 CFM continuously for the year. And so the cost of operation is $11,600, and of course we get the minus 40 dew point. Exhaust purge, that's where we add the heating capability. We get that vent rate down to about 7%, 7 to 8%, something like that. And we see the cost fall to about $8,000. The blower purge, we now are not using compressed air at all, but we're taking ambient air and heating it up and then using that for regeneration. That will get us down to about $7,000 per year. And the heat of compression type desiccant dryer is by far the most efficient. That gets us down to $2,000 per year. All the desiccants have the minus 40 dew point. The problem with a heated compression dryer is, though, it requires a lot of modification to your air compressor packages in order to be able to take your air directly from the compression element through the regenerating desiccant bed and then back into the aftercooler. And so that's an additional complication that a lot of times is not possible. Or certainly people are not worth to go to that extent to implement that type of dryer. In slide 117, we're looking at the relative position of the air compressor, the storage tanks, receivers, and the dryer. In this configuration, we are going to store wet air coming directly out of the air compressor package, and then let that reservoir stored air feed into the compressed air dryer that then the air goes out and feeds the distribution system. So there's good and bad to the relative position of the receivers and the air dryers. In this case, the air will have some residence time in the receiver tanks, and it can cool down. As it does, it will condense out some moisture, and so it will also perhaps drop out some lubricant that would have potentially gotten into the compressor package. Now, there should have been coalescing type filters to catch that, but sometimes those are not operating effectively, or sometimes they're not present. So I would say the good points of this arrangement are that we do some additional moisture removal and potential oil collection if it's a lubricant injected compressor before the air gets to the compressor package. The downside is that if we get a large surge in compressed air demand, perhaps more air can be pulled through the dryer than it has the capability to really dry and condition properly. We can have moisture surges out in the system for short periods of time. So, because it is certainly possible, if that's say a 1,000 SCFM dryer, if a lot of big uses open up at the same time, we might pull 1,200, 1,500, 2,000 SCFM through that dryer that's been stored in those storage tanks for a short period of time. And during that transient, there's no way that dryer can effectively get all that moisture out. So we'll see a surge in moisture content and dew point out in the system. Now, whether that causes a problem or not just depends on the temperature in the pipe and whether or not that moisture actually condenses. Moisture that stays in the vapor state typically does not cause a problem in most compressed air applications. In this arrangement, we see the dryer is located directly after the compressor package, and then it feeds dried, conditioned compressed air into the storage or receiver tanks that then feed the system. This is probably the more common arrangement, although I should note that it's possible to have storage tanks on both sides of the compressor so that we get all of the good points and none of the downside. The rule of thumb is that compressed air storage capacity never hurts you. The more receiver capacity that you have in the system, the better. Now, in this arrangement, however, since we are storing dried air, if we get a large short-term increase in compressed air demand, we will satisfy that with air stored in those storage tanks, and since it's dry conditioned air, we would have no spike or surge in dew point and moisture content out in the system during the transient. The downside is that we don't get any additional benefit in terms of lubricant or moisture removal by the storage tanks before they go into the dryer, as we saw in the previous arrangement. We'll now have a brief discussion on different types of filters that are commonly used in compressed air systems. We have particulate filters for the removal of solids, coalescing filters for the removal of liquids, and adsorption type filters for the removal of vapors. Compressed air filters are sized by flow rate and pressure drop. We always have pre-filters to remove particulates before we draw air into an air compressor. That's what the filter element on the left is. We simply sets at the suction to the compression elements, and the air is drawn through that filter, which removes the particulates. And then on the right-hand side of the slide, we see a coalescing type filter that pulls the inlet compressed air or gas into it across filtration elements. And then we have drains in order to be able to remove moisture from the filter itself, and the dried gas goes out the other side. This slide just shows photographs of different common types of filter units seen in compressed air systems. On the lower right, we see what we call a filter, lubricator, and pressure reducing station. You often see those, they're fairly small, compact units right before a hand tool or an end use. We're now ready to move on to condensate drain traps. And condensate drain traps are used to remove liquid water from the piping and distribution system. We have basically three different types. We have float type traps, electronic solenoid, activated traps and then manual traps. And we'll look at several different actual types of these in the following slides. Here we're looking at some general discussion related to different types of condensate drain traps and their proper application in the compressed air system. The first bullet point says avoid manual or open drain pipes. Manual valves can be made to work. However, experience shows that either people forget to open the valve at all and condensate backs up into storage tanks or potentially even into equipment, which causes negative consequences on the operation of the compressed air system. Or more likely, it becomes too burdensome to make it around the plant every day or every couple of days and crack these valves or open the valves, drain out the condensate, and close them back. So what happens is people just decide to, well, I'll just crack the valve open a little bit. And so then it becomes a compressed air leak that sits there and drains. It drains moisture, but it also drains compressed air from the system all of the time, and that's expensive. We also have timer-operated drain traps, and basically a timer trap is a leak on purpose. We'll see some pictures of them and talk about them more in future slides. But basically there's two dial settings. One tells the trap, okay, how often do I initiate a blowing sequence? And you can set that from, every 15 minutes, once an hour, once every 2 hours, 3 hours, whatever. And then the second dial says, okay, once it's time to open up and blow, how long do I stay open? That can be from just a few seconds up to 15 or 20 seconds or potentially even longer. So a time drain trap is a leak on purpose. Mechanical float type traps can work, but after a fairly long period of time or after they've been out in the field and have some experience on them, they tend to stick, either open or closed, and they lead to maintenance issues and reliability issues as well. So they're not strongly recommended. And the other type would be the solenoid type trap that automatically opens in the presence of condensate and stays closed the rest of the time. They're called zero loss traps because they don't waste any compressed air, and they are certainly recommended. Purchase price on those may be $1,000, $1,200 by the time you get it installed. On the time drain traps, it's a couple $100. So there is first cost incentive to go to the time traps. However, a lot of time traps are just a lot of leaks programmed into your system on purpose. Here we see images of two different types of traps. The zero loss drain trap on the left is an excellent drain trap to use. It has a small reservoir inside the trap that will fill up with condensate. When it reaches a high level point, the solenoid will open and the compressed air pressure from the system will drive the condensate out of the trap into a drain line. Typically, this can't be dumped directly because it probably has compressor lubricant in there, so that moisture has to be conditioned, purified before it can be disposed of. And then the time drain trap, kind of a schematic diagram is shown on the right-hand side, where you see the two dials. Like we said, one would set how often we initiate the trap to open, and the second dial would say once it's time to initiate that sequence, how long should it stay open. And there's some lights that indicate some little LED type lights that light up to tell you when the trap is operating, when it's not. You can typically hear these things when they're open, so it's not hard to tell when they're operating. This is a very common sight in many compressed air systems. What we have is a storage tank located outside the building. You see the hand valve. That's the way that they used to blow the moisture out of this tank. However, to their credit, they at least put an additional pipe extension on that, tied a timed drain trap into it, and then we see the discharge side of the trap going up to this big barrel, and you can see just a little bit of the side of the barrel on the left-hand side of the photograph. So that barrel, when it gets full, that has to be taken out and taken to water treatment before we can just dump it, because like we said, if that's a rotary screw system, lube injected compressor, you're going to have some compressor lubricant appear most likely in that condensate coming out of that storage tank. We see a smattering of leaves and old coffee cups and a few other pieces of debris around. This is not uncommon at all. There would be some energy savings related to replacing that timed drain trap with a zero loss trap. In slide 126, we're looking at photographs of some different types of zero loss condensate drain traps, and the note says that we can even get these with some built-in electronics that will sound an alarm if the trap should fail and not operate properly. Again, this slide shows a pretty good photograph of a zero loss condensate drain trap. Again, the reservoir fills up on these traps, and when it gets to a high level sensor, the solenoid valve opens and we force the condensate out. Once the condensate drops to a low enough level, there's another sensor, and it closes the solenoid valve. So proper operation will lose no compressed air. Should be vented from the system. A timed drain trap is shown in slide 128, and we see the two settings. We see that if you look at the two dials, the dial on the right shows that the cycle initiates every 15 minutes, and the dial on the left, it's set for the maximum open time of 10 seconds. And so if you want to know how much air is being vented from this trap over the course of a year, it's a fairly simple calculation. So we see that in 1 year there are 35,040 15-minute periods. So that's the number of times that the trap will initiate a sequence. And then it's open for 10 seconds for each one of these blowing sequences. So that's 350,400 seconds, or 5,840 minutes, or 97.33 hours. The air that's vented is worth about $400 a year. A zero loss trap would cost about $1,000 to install, yielding about a 2.5-year payback. Now, the payback depends on actually the size of the orifice in these traps. So if you want to do a calculation like this, not only do you have to figure out how many hours per year the trap will be open, but you have to estimate what's the CFM, what's the airflow rate through the trap when it does open. And typically you would look for an orifice size stamped on the body of the time trap. Would give you a good indication. And then with the pressure difference across the trap, you can go to a leak table and figure out about what the leak rate would be. These photographs were taken at the Ford small engine truck manufacturing facility outside of Detroit. And it may be a little hard to read on the photograph on the left. This is on their main compressed air lines that are feeding the particular building that was assembling these small pickup trucks. And in green, there is a tag, a formally printed out sign or notice on that moisture separator that says, "Do not close this valve." So the intent, there's no drain trap there, so the intent is to drain the moisture from that system, but also to have a significant compressed air leak all of the time. Not very efficient operation. Well, what happened is somebody decided that the compressed air leak was not acceptable, and so they closed the valve. Well, So much moisture was being generated in that system. It was a huge system, like, I don't know, 35 to 40,000 horsepower of compression capacity operating all of the time, distributing compressed air over the entire site. So it was a massive compressed air system. But the air was not dried at the location of the generation of the air. It was supplied wet into the piping system, distributed out to the buildings wet, and then was dried as necessary at the point of use. Well, that was a terrible idea. And so what happens is this valve sometimes gets closed, and so much moisture backs up into the system that eventually it flooded the compressed air system and knocked the entire production line down. And it was down for 4 to 6 hours that day. I rode with the engineer that went out, and he knew exactly where to go. Open that valve, and we probably drained 15 to 20 gallons out on the ground before it pretty much came to a stop. It drained for 15 or 20 minutes, or maybe even longer. Tremendous amount of moisture inside the lines. Also causes the lines to rust and corrode, which then that corrosion product, the rust, exfoliates, travels with the compressed air, gets down inside of orifices and control devices, and just causes all kinds of maintenance issues. Bottom line is the compressed air should be dried at the point of generation, and then this problem would cease to exist.
We're now ready to move on to the compressed air distribution system, and in this portion of the workshop we'll look at design and maximum allowable velocities of the airflow inside the piping system. We'll also talk about some sizing criteria. We'll look at pressure drops per 100 or per 1,000 foot of pipe based on compressed airflow and pipe diameter. We'll look at fitting losses, how to take particular elbows and components and turn that into an equivalent length of pipe. And then we'll close with a summary and some suggestions for good piping design.
An integral portion or component in any compressed air distribution system would be the storage capacity or receiver tanks that are installed. We see just a variety of different photographs here. They can be horizontal, they can be vertical. They just have to be a rated pressure vessel. We've actually seen people take old railroad cars and the tanker cars that are rated at pressure, and have that brought over and set, the tank actually taken off and set outside the plant. My recollection is that was about between 30,000 and 40,000 gallons of storage. It's an excellent idea. The tank has to be cleaned to the point that you're not going to introduce, foreign matter or particulates or corrosion products into your compressed air piping. But beyond that, it's a super idea. All compressed air systems need storage to smooth out pressure fluctuations caused by intermittent demand. The demand in most industrial facilities moves around a good bit. Large uses, filters get blown down, all kinds of different uses for compressed air are intermittent. They start, stop. 2 or 3 big users may just open at the same time, which can contribute to large changes in flow as well as pressure fluctuations in the system. The more storage that you have, that will means you have compressed air stored at pressure, and it's available to smooth out and dampen any pressure fluctuations that would be caused by this erratic rate of use of compressed air. Lubricant injected rotary screw compressor systems need 3 to 10 gallons of CFM, gallons per CFM of trim compressor capacity. We've seen that in the discussion on the generation. Certainly, the more storage, the more efficient load-unload operation you can have with a lubricant-injected rotary screw air compressor. The old adage is more storage is better. It's a one-time cost, and you reap the benefits for every hour that you operate the system. And you can consider secondary or dedicated storage for high volume, short duration applications. If you have one particular use that is really large, you can put a dedicated storage tank. What you typically do is put an orifice on the fill line to the tank so that the tank fills slowly, and then when that particular application opens up for maybe 15-30 seconds, instead of draining down system pressure, you preferentially drain the air out of that compressed air storage tank, which is sized to be able to support that load, and then the operation of that one large use as it happens intermittently does not really affect the pressure in your overall system. It's a very excellent idea, and one you should consider if you're having pressure fluctuation problems, especially if they're initiated by just a couple of large intermittent users. When considering a lube-injected rotary screw compressor, the amount of time the compressor can stay unloaded on the unload portion of the cycle is dependent upon the amount of compressed air usage from the system and the amount of compressed air storage or receiver capacity that is provided relatively close to the compressors. As we see here, for most of the time, there's not sufficient receiver capacity to allow the compressor to unload for significant periods of time until we get to a portion of the day where the compressed air demand is drastically reduced, in which case the relative amount of storage compared to the amount of air that the compressor is producing is very large, and we get pushing a well over 2 minute unload period. And we see the current fall significantly lower when the compressor can stay unloaded for these extended period of times. This long unload portion in the center of this is what we need to strive for all of the operating cycles in order to improve the part load efficiency of this compressor. This slide from the compressed air challenge is a duplicate. We discussed this earlier, but it's very important, and it's in here a second time to emphasize the impact of the receiver capacity in the system, i.e. the gallons of storage per CFM of capacity of the trim compressor, or the compressor that's going to respond to load changes in the system. And we see that the top curve here is not a very efficient unloading curve, and that's what you're going to see with basically 1 gallon per CFM of storage capacity. And that refers directly to the fact that it takes 40 seconds to blow the sump down, and the current on the system, the electrical current usage or the power draw on the system does not fall until we get the pressure blown off of the sump. And so the current just never has time to fall to its lowest level, so we don't unload very efficiently. And then the best curve, the bottom curve, represents 10 gallons per CFM of storage. And we see that is starting to approximate a straight line. And so we're getting significant unload periods. Again, the rule of thumb is we need to be able to keep the compressor unloaded for 2 minutes or more for the unload portions of the cycle. When sizing an air receiver or storage tank, we use this simple equation. And the various parameters in the equation, the V would be the required volume in cubic feet, and that can be calculated by taking T, which is the time interval in minutes of which we wish to blow down the receiver tank from its initial storage pressure to the minimum pressure which we can allow in the system, times the quantity C, which is the required delivery of airflow from the system in free cubic feet per minute, minus the cap, CAP, which is the compressor capacity. So the difference with those would be the deficit that we have to make up from the storage tank. And P sub A is just the absolute atmospheric pressure in pounds per square inch absolute. P1 in the denominator is the initial tank pressure, and P2 would be the minimum tank pressure, or the point at which we say that we have basically expended the useful compressed air storage in the storage tank. We're going to have a air receiver sizing example, and for this example system we have two 200 horsepower lubricant injected rotary screw compressors present. The compressed air use is basically steady at 800 CFM, except for one occasional short-term large use, which is to blow down a filter, and this occurs once per hour, and the duration of this use is 15 seconds, and it requires 600 CFM to blow that filter down. So the idea here is, if we don't have dedicated receiver capacity to handle this filter blowdown, we're going to wind up running both air compressors, even though one of the air compressors can easily handle the 800 CFM load. And if there was enough storage and we could slowly charge the storage tank, the one air compressor could be run the entire period of time. But without the storage, in order to drastically pulling down your system pressure for this 15-second filter blowdown every hour, you're going to have to run both air compressors. Okay, so the point here is to size a storage tank to supply that 600 CFM use and operate just the one compressor. System pressure is maintained at 100 psig nominally, and we can allow it to briefly drop to 85 psig without causing a big problem in the plant. Continuing on with our air receiver sizing example, the ambient air pressure is assumed to be atmospheric at sea level, which would be 14.7 pounds per square inch absolute. The 15-second duration of the filter blowdown is converted into minutes by dividing by 60, and so that's 0.25 minutes. And so then we plug the known information into the receiver sizing equation that we discussed on the previous slide. And so we have this 0.25 minute transient. During that period of time, the air demand on the system is 1,500 SCFM, and the capacity of one compressor is, one of those 200 horsepower compressors is about 950. That time the 14.7, and our initial system pressure is assumed to be 100. That's what we're maintaining, and we can allow the system pressure to drop to 85 without causing a huge problem. And so the calculation of the equation results in 110.25 cubic feet of storage, and that's 825 gallons. And so we would probably err on the side of making the tank a little bit larger. And so I would probably recommend a 1,000 gallon storage tank be located very close to that filter. Here we're looking at a second example on sizing secondary storage, or a secondary receiver tank. And it's a slightly different interpretation of the input variables. The net result is the same calculation as previously. So let's go through this one briefly. Compressor capacity is 350 ACFM, actual CFM, into the machine. The discharge pressure is maintained at 100 psig. The steady process demand in this case is 300 ACFM. So from the average demand, the compressor has an extra amount of capacity of 50 ACFM that could be available to respond to an increase in demand. The intermittent demand that we are concerned about is an additional load of 100 CFM that occurs for 10 minutes per hour. Okay, So the peak demand is when we have our steady process demand of 300 plus this intermittent demand of 100, so we're up to 400 ACFM. We can calculate the average demand over the time interval. So we have the 300 ACFM times the 60 minutes per hour, because it's continuous for the full hour. Then the 100 ACFM is only for 10 minutes, so that's the 100 times 10, and then divide that by the 60, and so we get a kind of weight averaged demand, including the intermittent demand of 316.7 CFM. Pressure at intermittent demand point cannot be allowed to fall below 90. So in this case, if we charge the receiver tank to 100, we actually have 10 usable pounds per square inch of pressure that can bleed off of that tank, or air stored in that tank in terms of the elevated pressure above the 90 that can help us maintain the system pressure during the intermittent usage. Okay, and then we show the equation. It's the same basic equation. This time we've changed the variable names a little bit. So again, volume is still the required receiver volume in cubic feet. T is the time for the required pressure drop of 10 psi to occur, in this case 10 minutes. C is the intermittent demand, is now the interpretation in this application. So that's the extra 100 on top of the steady process demand. S is the compressor capacity minus the standard, or the average process demand. So that's the 350 compressor capacity minus 300 is equal to 50. Again, PA is the absolute pressure of the atmospheric air, and P1 is the initial receiver pressure, and P2 is the lowest acceptable receiver pressure. We're now going to plug the values from the previous slide into the sizing equation and actually do the calculation of the required receiver volume. So we have the time of the intermittent demand is 10 minutes. The level of the intermittent demand above the average is 100 ACFM, and the extra compressor capacity that is available above the standard demand, it was the 350 minus the 300, or 50 ACFM. So then that quantity is multiplied by the atmospheric pressure. So we've got 14.7 pounds per square inch absolute, and we're going to divide that by the initial receiver pressure of 100 minus the 90, which is the lowest allowable useful pressure in the system. So that's the 10, and so the result of that calculation is 735 cubic feet of receiver capacity. In slide 140, we are going to turn the equation around and calculate the amount of time that it will take to recharge the receiver tank from the system. And so we now use the 735 cubic feet of receiver volume. We multiply it by the allowable pressure drop, or in this case it's the pressure increase from the 90 pounds per square inch back up to the 100, and then we divide that by the quantity, the total compressor capacity minus the average demand, which turns out to be 50, times the absolute pressure of the atmospheric air, 14.7, and the result of this calculation shows that it takes 10 minutes to recharge the tank. Now, I will say that most of the time we would put an orifice in the fill line on the compressed air side to allow the tank to fill over a longer period of time and restrict the airflow into the system to make sure that we didn't upset the pressure in the system during the refill operation. So that's kind of common, something you need to think about. In this example, it doesn't look like that's really necessary, but for a larger tank, that on the discharge side or the refill side, involving larger airflows, you might want to restrict that to make sure that you didn't refill it too quickly, and if you had some other transients going on in the system, perhaps experience a lowering of the system pressure. In this slide, we've turned the equation around one more time to show that if we have a receiver tank that we know the volume of, and we know our initial and allowable minimum system pressure, we know the absolute pressure of the atmospheric air, and we have a time duration over which we wish to discharge this tank, we can then calculate the useful, usable airflow rate out of the tank. In this case, it returns to us the 50 CFM that we can deliver on average from this tank into our system to help support system pressure during the transient demand. We now have a small section of the workshop which looks at the pressure drop as the compressed air flows through the piping and the distribution system. We'll talk a little bit about acceptable and unacceptable air velocities and look at pressure loss through different components and straight pipe. Our compressed air piping and distribution system should be sized for the lowest possible pressure drop. And of course, as the diameter of the pipe increases, the cost on the system increases. And so we have to do some pretty careful analysis to get the pipes as large as possible to reduce the pressure loss, which translates into operating energy cost. But that has to be balanced with the first cost of buying and installing the system. If we look at some typical or some desired pressure losses through the system on our main distribution piping, we see it should be about 1% or no more than 2% pressure drop. And so if we look at 100 psig discharge pressure, which is just kind of a nominal value, we would expect to see a 1 to 2 pound drop across our main distribution piping. Branch piping could be 2% to 3%, or that would translate into 2 to 3 psig drop on a 100 psi system. Pipes need to be pitched to handle any liquid condensate that occurs in them. And so the recommended pitch is 1 inch per 100 feet of pipe, and that should be sloped towards a drip leg that is connected to a condensate drain trap. Hopefully a zero loss trap would be good. Dryer should be sized appropriately for the maximum compressed air demand that would go through them that they would have to handle. And we of course need to pay attention to the pressure drop on the dryers. Filters should be sized by flow rate and pressure drop, certainly not the size of the pipes that are connected. Gauges are pressure gauges are placed strategically in the system. We want to be able to monitor the pressure drop across all compressed air system components, and consider connecting your pressure gauges with quick connects to make it easy. The gauges will need to be replaced periodically, and it makes it a whole lot easier if you can just quick connect those into the system. Leaks, we have planned leaks. That could be a timed drain trap, and we certainly have unplanned leaks, which occur fairly consistently throughout all compressed air systems, and so we need to control those because the increased compressed air flows through the system just cause the pressure drop to increase to higher numbers than they would be otherwise. And all low pressure connects or quick connects should be purchased with pressure drop in mind. Sometimes we purchase a 1/4 inch when we could pay just a little bit more and get 3/8 or 1/2 inch that have that, and also the hosing or tubing that goes down to, say, a hand tool. The larger diameters have far less pressure drop, and that can allow us to run the system at a lower pressure that can reduce the energy requirements at the compressors. This slide shows a table of friction losses through straight pipe. So this would be the loss of air pressure for a 100 psi system due to friction, and the numbers represent pounds per square inch of lost pressure per 1,000 foot of pipe. And so we have a column on the far left, which is the delivery of compressed air in cubic feet per minute, and that is at pressure at the 100 psi. The second column from the left is the equivalent delivery of compressed air in terms of inlet capacity to the compressor, which is how most compressed air flows are actually denoted. And then we have the different pipe diameters, the nominal diameter from 1/2, 3/4, 1 inch, all the way up to 12 inches. And then we see, for example, the first entries in the table on the left would be if we have 40 SCFM of air delivered to a load, the compressed flow rate is only 5.12. But in a 3/4 inch pipe, that would cause a 16 pounds per square inch drop over 1,000 foot of piping. That's probably not acceptable. That's pretty excessive. So the next step up in pipe size would be to 1 inch, and we would see that pressure drop go down to 4.45 psi per 1,000 foot. That's probably still a little bit on the high side. Of course, it depends on how large and extensive your distribution system is as well, but I would say we would probably be in the 1 1/4 to 1 1/2 inch range. At 1 1/4, we see 1.03 pounds per square inch drop per 1,000, and at 1 1/2 it goes down to a little less than a half, or 0.46 psi per 1,000 feet. So that's kind of how we work with the table. So for example, let's say we had 1,000 SCFM load. We can run down the table to the 1,000 in the second column from the left and run across. That would put us in either 4 inch or 4.5 inch pipe. We're probably not going to be buying 4.5 inch pipe, so I would say that's probably 4 inches of pipe, which would have a pressure drop of 2.21 inches per 1,000 feet. Now, that's probably going to be acceptable. If we had a very large distribution system and we wanted to minimize it, we might wind up with 5 or even 6 inch pipe, but that's probably going to be too expensive. So we probably would swallow that 2.21 inch pressure drop per 1,000 feet and live with it. In this slide, we see just an alternate presentation of the same type of information. What we have here is a log plot that shows free airflow in CFM, so that's the inlet airflow into the compressor at basically atmospheric, or a lot of times that's calculated at 14.5 pounds per square inch absolute. And then the pressure drop in, this is PSI per 100 feet. So to compare to that previous table, we would need to take these pressure drop numbers and multiply them by 10, because the table on the previous slide was pressure drop per 1,000 feet. And so you see we've circled in kind of a red oval down at the bottom. This would be the desired design range. And it's someplace between 0.1 and 0.3 psi drop per 100, and so that's going to translate into 1 to 3 psi drop per 1,000. And then we've got curves for the different pipe diameters from a half up to 4 inch. So this is the same sort of information, but you kind of see how if you try to cram just way too much airflow through a given pipe diameter, how the pressure drop can become excessive. I mean, if we were trying to put let's say a 1,000 SCFM through through a fairly small pipe, we could get up in the order of 5 to 10 psi per 100, and so that's 50 to 100 psi per 1,000. That's obviously unacceptable. This slide is addressing pressure loss through screwed pipe fittings, and what we see here is we can, for each fitting, we can turn it into an equivalent length of straight pipe, and so then we can, when we're doing the pressure drop calculations, we can add up the amount of straight pipe with the flow rates through them, calculate pressure drop for that, and then for each fitting we can add a certain additional of equivalent length of feet and include the fitting losses in as well. So for example, let's look and say that we have some 2-inch nominal fittings, and so we can look over on the far left. That's the nominal pipe diameter in inches. We see the actual pipe diameter, just kind of FYI. And then we have the different components. So we have a gate valve, a long radius elbow, a standard radius elbow, an angle valve, a close return bend, a T through side outlet, and a globe valve. And of course you can find many additional type fittings and similar tables in the literature and sizing handbooks, that sort of thing. So for our 2-inch, let's say we're comparing long radius elbow to a standard elbow. So at 2 inches, the long radius elbow is equivalent to about 2.07 feet of additional length, and the standard elbow is 5.17. And so we see that if we have room and can utilize long radius elbows, it's going to help us significantly on our pressure drop through those particular components and the system as a whole. We now move on to a discussion of air velocity inside the compressed air piping or distribution system. Recommended air velocities inside the compressed air pipes are between 20 and 30 feet per second. A common design value is 20 feet per second. That will minimize your pressure losses. You get much above 30 feet per second and the pressure losses start to rise fairly dramatically. The ACFM through a pipe section is divided by the compression ratio using the absolute pressures to determine the volume flow rate at pressure inside the piping. So for example, in the previous tables, we had, let's say, an airflow of 100 ACFM, that's actual CFM into the compressor, translates over to about 12.81 CFM that's actually flowing through the piping system. So it would be the 12.81 that we would need to address in the calculation of velocity inside the pipe. And so in order to get that, we would take the pressure ratio, and so that would be let's say if we had a 100 psi system, that would be 114.7 psi absolute, and we divide that by the inlet pressure at the compressor, which might be a lot of times that's considered to be 14.5. So then we take the result of that division and multiply it, or in that case we would divide the 100 by that and get the little over 12 CFM that's flowing inside the piping system. We now have an example to calculate the actual velocity of compressed air flowing through a section of pipe. So for the example calculation, we have 1,000 ACFM, and of course that's the actual condition entering the compressor, and it's flowing through a 3-inch diameter pipe at 100 psig, and we're going to take the standard inlet pressure of 14.5 psig. So as we move into the calculations, first we calculate the cross-sectional area of the pipe, which is pi diameter squared over 4. And so the pi is 3.14159 times the diameter, the 3 inches, divided by 12, because we have to convert to feet. And so that's squared and then divided by 4. So we get a cross-sectional area of 0.0491 square feet. The compression ratio is calculated as the 100 psig plus 14.7 to get psia, and then we're going to divide that by the 14.5, which is considered the standard inlet pressure to the compressor. So that would be on the discharge side of the inlet air filter. And so the compression ratio calculates out to be 7.9103 in this case. And so then the volume of flow at pressure inside the pipe is the 1,000 ACFM divided by 7.9103, or we get 126.42 CFM at a pressure of 100 psig. So then the velocity in the pipe will be the 126.42 cubic feet per minute flow divided by the cross-sectional area of 0.0491 square feet, and then we're going to convert from minutes to seconds, and we get a velocity of 42.9 feet per second. And we said that the highest velocity that we really want to see inside the piping is 30 feet per second. So we're 12.9 feet per second above that. So this is too high. We're going to have excessive pressure drop. And so we really would need to put this through a 4-inch diameter pipe. And if we go back to the pressure loss table several slides back, we see that the table shows 9.3 psi drop per 1,000 feet of pipe. And again, we would conclude that that is too much. This slide shows a repeat of the table showing pressure losses for different flow rates and pipe diameters. And we've simply circled the 9.3 number to make it clear where that came from on the previous slide. When operating a compressed air system, it's a good idea to periodically chart out your system pressure profile, and that's what is shown in this slide. And so we see we have an operating pressure band at the top of the figure that operates between 100 psig on the low side and 110 psig on the high side. So for the rest of the discussion, we're going to be assuming that the discharge pressure is 100 psig. We then look and we measure the dryer and filter pressure drops, and we see that on this particular day we got 10 psig drop across the dryer and filters up around the compressor room. That might be considered excessive, and of course if we've done this numerous times, that might be the best we can do. But at first blush, if that was my system, I'd be questioning why do I need 10-pound drop across my dryer and filters. At any rate, then we hit the distribution system at 90 psig, and we see that the main lines out through the plant, we see a maximum of 5 psig drop. Again, that's fairly high, a little bit on the high side. And then we get down to the the branch distribution system and into the actual end users. We've got filter, regulator, and lubricators that have pressure drop, valve, hoses, quick connects, and all that sort of thing is contributing another 15-pound drop. So this is a little bit of a cartoon of a system, but if this was my system and I saw these numbers, I would think that I had some opportunity to take some pressure drop out of the system, which then could lower the pressures in your pressure band. That could save you some money on compression energy at the compressors. Proper system maintenance certainly plays a role in minimizing and keeping the pressure drop of your distribution system under control. Certainly we need to change air oil separators and filters before they reach their maximum pressure drop. This will typically pay for itself. Change system and component line filters before they reach their change indication, or certainly right as they're approaching it. And let's keep the inlet filters, intake filters on the air compressors clean. There are lots of horror stories out there in the industry. Especially you have to be careful if you're drawing compressed air, say, from above the roof, and you might have a 6 or 8 or 10-inch line coming down. It's very common to have some pre-filtration up on the roof that people may not be aware of, and then you actually have additional inlet filters at the compressors. But the ones up on the roof, sometimes people don't realize are there, and they can sit up there for a number of years without attention until we start generating problems in the system, which eventually lead us to the roof to diagnose. Here we're looking at a block diagram of a simple compressed air system, and the idea is that just to indicate typical locations where we would want to be able to take pressure measurements in order to be able to evaluate the condition of each of these elements, and that so we can monitor and make sure that the pressure drops in the system don't become excessive over time due to perhaps inadequate maintenance or maybe we've just simply forgotten or we've missed a period or two where filter elements should be changed, etc. Or something's happened in the compressed air dryer. Sometimes these flow paths just become partially occluded with dirt, debris, corrosion products that exfoliate, whatever. And so at every point, we've got P1 through P5 would just be an example, but across every component that could develop a pressure drop, we need to be able to take measurements to evaluate. All right, now we're going to have a brief discussion of compressed air leaks. And yes, dare I say it, if you have a compressed air system, you probably have some leaks. It's just usually not possible to eliminate on any sort of an ongoing basis all of your leaks. The rule of thumb is that a world-class compressed air system of any size will leak around 10% of the air produced. If you can get to or even under 10%, you have done an outstanding job in leak detection and repair. The compressed air leak rate in a typical industrial system is usually on the order of 20 to 40% of the compressed air generated. The goal should be to reduce compressed air leak rate to less than 10% of the air produced. Leaks can actually be planned or unplanned. Air used to eject parts, say, in a stamping operation would be a planned leak. Leaking fitting or cracked hose or something broken in the system would be an unplanned leak. You should certainly use good quality hoses and disconnects, and of course increasing the diameter of those will reduce the general pressure loss through those components. We need to replace cracked filter bowls, and we need to develop a good leak remediation plan or bring in experts. There are plenty of people that specialize in compressed air system maintenance that can help in this. And if you are operating in the Tennessee Valley, where TVA is the electrical provider, you can request through your local electrical distributor a free compressed air leak survey. TVA will bring in ultrasonic leak equipment and find and tag your leaks. Unfortunately, they will not repair them for you. However, that's your part of the program. Here we have a depiction of kind of a very simplistic compressed air system, and different locations that might be prone or susceptible to developing leaks are tagged throughout that system. So you can look through all of those and just get some kind of an idea. If you were to start a compressed air leak survey, you would want to be sure and check these, as well as just walk down the entire system, hopefully with an ultrasonic leak detector, to be able to listen for smaller leaks that can't be heard with the unaided ear. And then off to the right side, we have a depiction of three different round hole orifice sizes: a 1/16, an 1/8, and a 1/4 of an inch. And assuming electricity costs 5 cents a kilowatt hour, which most people can't buy it for that anymore, and that we have a fairly efficient compressor, we see the relative cost of that, the compressed air that would leak through those different size orifices. So for a 1/4 inch, we're $8,382. So $8,000 to $10,000 a year would be the cost of that, if that was allowed to go on for a full calendar year. So we can see that it doesn't take a very large compressed air leak to be able to run into some money in terms of the compressor energy to make the air that gets leaked. Now, I should just recall back to different portions of the course. If you fix that leak, that may be the value of the compressed air, but the savings really are determined by how the compressor unloads. And so if we have a good part load control strategy on the air compressor, we fix a bunch of leaks, yes, it translates into good dollar savings. If we have a very inefficient control strategy, such as modulation or suction throttling on a lubricant injected screw machine, we can fix a bunch of leaks and we don't save very much. If we had a centrifugal compressor with a blow-off valve already open and we fixed a bunch of leaks, we'd simply reposition the blow-off valve and we wouldn't save any money. So it's always good to fix your leaks, but you got to be a little careful in predicting the financial impact. You have to look at how the compressor operates. Here we have a compressed air leak rate table, and this particular table is keyed for 100 psig compressed air pressure into the leak. And we've characterized different leak size by different orifice sizes. And you need to recall that a sharp-edged orifice will pass 60% of the flow of a dull-edged orifice. And so when you're putting together these tables, it's conservative to go ahead and assume that the leak behaves as a sharp-edged orifice so that you don't overpredict the compressed air loss. And so we've got a compressed air leak rate in SCFM versus orifice diameter from a 64th of an inch up to a half an inch. And then for various, actually we have it for various inlet pressures, 70, 80, 90, 100, and 110. So you can see how the leak rates change as the pressure goes up for a given orifice size. In slide 157, we have basically the same leak table as was described in the previous slide. However, instead of a leak rate, we have now translated the leak rates into the cost per year. And the assumptions here is that the cost of compressed air is 25 cents per 1,000 cubic feet. And the power cost here is assumed to be 9 cents a kilowatt hour, a little more updated than the previous numbers that were at 5 cents a kilowatt hour. And so we can see that if you had an eighth of an inch leak at, let's say, 100 psi system, that cost over $2,700 per year. So now again, the savings for fixing that go back to the part load strategy of the air compressors. In establishing and operating compressed air leak reduction program, there are certain points that are important to keep in mind. We need continuous system observation in order to find, detect, identify, tag failures or leaks. We need an annual focused compressed air leak survey where we get out at least once a year. And in higher pressure areas and areas that are prone to leaks, we may want to look more than once a year. We need a systematic investigation, say routes or procedures that we use. Certainly we have to identify all leaks in the field. We need to maintain a master database of the locations, the frequency, the severity, the size of the leaks. And we need to prioritize leak repair. Let's fix the big ones first that are causing larger economic loss. We need to keep in mind that traps and drains are very likely areas that can develop leaks and make those primary targets. And we can always invest in, for a couple $1,000s, we can get a good ultrasonic leak detector that will help find smaller leaks that may be difficult, especially in a noisy environment, to find without equipment to help us. As we've said previously, compressed air leaks produce not only significant waste in a system in terms of energy loss, but also can cause additional maintenance and cause equipment to deteriorate more rapidly than it would otherwise. Leaks are a significant factor in determining long-range strategies. If we can't get our compressed air leaks under control, we may be forced into purchasing additional compression capacity to be able to support the leaks and the legitimate uses as well. And again, just another little example, an eighth of an inch diameter leak can discharge 15 SCFM at a pressure of 70 inlet pressure, and that can easily translate to over $2,000 a year. A few more comments on the economics of compressed air leaks. We know that we need to fix the leaks, and again, this slide just brings up the point again that the savings depend on the part load operation of the compressor. You could save nothing. We want to reduce the leak rate. Really the holy grail of leak reduction is if you can actually shut off an operating air compressor. Say if we've been running 3, we fix enough leaks, we only need 2. There's huge savings in that. So in terms of a leak detection repair program, it doesn't get any better than being able to shut off one of your operating air compressors because of the leak program. And of course there is a difference between the overall cost of generating compressed air that's generally presented in dollars per thousand standard cubic feet, and the actual savings from the leak program based on the unloading of the compressors. A good place to look for compressed air leaks is often abandoned and unused equipment. Sometimes we take a piece of equipment out of service and we forget to disconnect the compressed air line going to it. Maybe initially it does not leak, but over a period of time gaskets can fail, the thing can get run into, whatever, and if there's nobody out there around it, it can start leaking. And sometimes these can be very large, even massive compressed air leaks that, depending on where that piece of equipment's located, if it's someplace that's shut down that we don't have personnel around, it can sit there a long time before somebody finally discovers it. In this slide, we just list some of the leak problem areas that we would expect to have to check closely on our leak surveys. Certainly couplings, hoses, tubes, and fittings. any disconnects, quick connects, that sort of thing are very prone to developing leaks. Filters, regulators, and lubricators, known as FRLs. There's lots of opportunity there. Open condensate traps, pipe joints, point-of-use devices, flanges, cylinder rod packing, control and shut-off valves, and threaded sealants, just to name a few. Here's a few rules of thumb. $200 a year for a leak that cannot be seen or heard, $800 a year for a leak that can be felt but not heard, and $1,400 per year per leak or more if it can be felt and heard. That's assuming about 10 cents a kilowatt hour. Again, we got a plug for ultrasonic leak detectors, and we've got our investigator out there in his Sherlock Holmes hat, pipe, and magnifying glass. We have mentioned this earlier, but this is a nice simple little equation that can be used to estimate your leak load with an air compressor that's running in load-unload strategy. And what you do is you find a period of time when you don't have any production going on, when there's no what we call legitimate use of compressed air, and all you're doing is feeding the leaks in your system. Now, some plants just can't do this. Some plants production is 24/7, and there's never a period of time where we're not using air for legitimate purposes, and if that's spread out all over the place, then you probably can't do this. But a lot of plants, maybe two shifted, maybe down on weekends, or maybe down on Sunday, something like that. And we can pressurize the compressed air system by operating a compressor, or hopefully one in load-unload, and then we simply time the cycles, where the capital T is the loaded time, and you can listen to it, or you can put a current data logger or a pressure data logger on it and log it for a small period of time. Then you can actually download that data and do very accurate calculations on this. You can do it with a stopwatch. You can do it with the stopwatch built into your smartphone if you want to. But anyway, so you just stand by the compressor and listen to it to load, and you start the stopwatch, and whenever it unloads, you note that time, and then you continue to denote the unload portion of the cycle until it loads again. So you've got two different periods, time periods, capital T, the loaded time, small t, the unloaded time, and you simply take the loaded time times 100 and divide it by the total time, the loaded plus the unloaded time, and that will give you the percent of the compressor capacity that is the leak rate. So if that turns out to be 25%, and you've got, say, a 100 horsepower compressor that's rated for, let's just say it's 400 CFM. It's probably a little more than that, but at 25%, then you'd say your leak rate is 100 CFM, and that's a pretty accurate determination, at least for that particular day.
The final section of the course is on compressed air uses, and here we will question and try to classify appropriate and inappropriate uses for compressed air. The general rule of thumb is that from an energy perspective, compressed air is the most expensive of the site utilities, and so if we're going to have some sort of a motor-driven application, it makes sense to try to do that with electricity instead of compressed air. Now you get into the situation where sparks are not permitted, and electric motors tend to generate sparks if you have any sort of an explosive atmosphere, and so that would be an appropriate use for compressed air. But if it's, for example, a stir on a tank of paint, perhaps, if that's being driven by a pneumatic motor using compressed air, it could be done much more cost effectively with an electric motor, and the results would be the same. So we'll look into that, and we'll question a lot of typical uses for compressed air. People like to blow themselves off, to blow off their workspace before they go home. That's one, a safety hazard, and two, it wastes money. So we will look at a lot of typical uses and try to classify those as to appropriate or inappropriate.
Here we're looking at air requirements for various types of tools, and this just kind of sets the stage for the discussion of compressed air uses, those that are legit and maybe are not so legitimate. But this just lists lots of different types of equipment that can use compressed air as an energy source, and we get some kind of an idea of the free air CFM usage. This can be handy in trying to evaluate the cost of the operation of a particular tool. And this slide is just a continuation of the following table with air requirements for various types of pneumatic tools. Okay, so here we have a list of potentially inappropriate uses for compressed air. Now, this is not to say that all of these are always inappropriate in a particular application or a given industrial setting. However, some probably are pretty much all the time, like the first one, personnel cooling, when you got your employees basically blowing themselves off with compressed air to get dirt, debris, dust, whatever off of them. That's not a good practice. It wastes compressed air, and it's also dangerous. You got 100 psi air, and you open that thing up, and it can drive stuff into the skin and actually cause damage. Of course, the guys out there in the field, they learn pretty quick the best ways to do that, but it's still not a safe practice, and it's still very wasteful. Parts ejection, idle equipment. We can use solenoid valves. Sometimes you can install a solenoid valve that will automatically shut off the compressed air supply to a particular line or a piece of equipment that might be prone to leaks, so that at least when the equipment's down over the weekend, that you're not feeding those compressed air leaks. Open drains, traps can fail open, or maybe there's not a trap and people have cracked a manual valve. That's a possibility. Sometimes we blow compressed air on hot spots just to cool them off. That's not really a good idea. It might be better to try to investigate and repair a bearing or whatever's causing the hot spot to exist in the first place. A lot of times we throw compressed air at problems because we don't have the time or don't understand what's causing the problem. We just know if I blow compressed air on it, I make the situation better, but that's a pretty expensive fix. Again, high delta P in components, disconnects, quick connects, flexible tubing, that sort of thing, cabinet coolers, air motors, air hose blowing, air vibrators, sparging of compressed air for mixing of tanks, and can sometimes done with electrical motor-driven mixers, diaphragm pumps, and many, many more. A potentially inappropriate use would be for sparging or mixing / agitating a tank with compressed air. We have a couple of examples here where you can see compressed air is simply delivered down to the bottom of a tank and blown out, and the bubbles churn up the fluid or the mixture to keep it mixed. It works very well. It could be that we could use some sort of a mechanical stir that might be driven by a small electric motor that could drastically reduce the energy use. Continuing our discussion of potentially inappropriate uses for compressed air, we have a couple general concepts here that need to be considered. First of all, low pressure applications can often be accomplished using blowers or fans. Single stage blowers can generally get up to about 20 psig or less, and two stage blowers can produce maybe up to 30 psig of air. It makes no sense to compress air to 90 to 110 pounds of pressure, distribute it through a system, and then drop the pressure to 5 or 10 or 20 pounds per square inch before we use it. That's an extremely inefficient and expensive process. It would be much better to install maybe a small blower close to that application and generate that low pressure air right there close to the end use. Work accomplished with inefficient air motors can often be done much more efficiently and cost effectively with electric motors. The one caveat there is we have to be careful about hazardous environments. The electric motors can cause sparks that could cause explosions or fires. So we have to be real careful. Now, there are some specialty motors that you can purchase that try to eliminate that, but in some situations, the compressed air really is the best choice for safety reasons. But beyond that, we should give a close look to getting rid of as many air motors as possible. And in terms of vacuum generation, we can often do that more efficiently with a vacuum pump as compared with compressed air flowing over a venturi or through a venturi nozzle that accelerates the air, creates a low pressure region, and then we connect the vacuum line into the low pressure region, and that causes the vacuum to occur. However, we're continuously venting compressed air in that process. So perhaps just a standard vacuum pump could accomplish that task more efficiently. In this slide, we just have a couple of photographs of some high-pressure blowers that, again, can produce air up to pressures of 20 to 30 psi-G, depending on the number of stages and the design specs on the particular blower. In this slide, we learned that these high-pressure blowers can achieve 30 psi-G air with only about 20% of the energy use of an air compressor, producing air at 100 psi-G, and then we reduce the pressure through a pressure-reducing valve. Here we're looking at a photograph of an air motor, and this will produce shaft power that can be used for any number of required applications in the plant. However, if this could be replaced with an electric motor, the efficiency of a small electric motor is probably between 80 and 85%. The efficiency of compressing air for the energy in, the pressure energy we get out, is probably on the order of 10%, something like that, depending on the compressor and the controls and all that sort of thing. But you might get 15% operating at completely full load. But beyond that, using the electric motor from an energy perspective is just a far better. In slide 174, we see a schematic diagram describing vacuum generation using compressed air. And the compressed air comes into the device and flows through at a very high rate of speed. When it flows over the top of the line coming in perpendicular to it at the bottom, it traveling quick, at a high speed across the top of that will basically pull air out of the vacuum line, and it is that action of pulling the air out that creates the vacuum inside that line. And it's a very simple device. That's how the vacuum is generated. Again, the cost of operating this is the cost of producing the compressed air, and then both streams exit at the right side of the device together. In this slide, we see a couple of photographs of air wands that are used to blow off any potentially needed application. These things get used to blow off people and clothing and floors and workbenches, which is not particularly a good idea and can be a safety hazard. So there certainly are appropriate uses for these types of devices, but there are also plenty of inappropriate uses as well. We typically have a quick connect fitting to attach to the tool itself, and then we just have a hand valve and handle. And the more you depress the lever, the more pressure you put to the air flowing through the device. And completely open, we can put pretty much line pressure through these devices, unless there's some sort of a regulating valve on the inlet, which is not usually the case. So a bunch of these things operating at the same time can use up a lot of compressed air. It is possible to put induction nozzles on these devices, and we'll speak a little bit further in the workshop about what an induction nozzle is. We now move on briefly to look at a compressed air diaphragm pump. This is basically just a pump driven by a specialty air motor, and you can look at the various components that are on the called out on the right-hand side. We've got letters A, B, C1, C2, D, E, and F, and you can look at that, but basically what happens is we apply compressed air to one side of a diaphragm that then moves it over, moves its position, and that motive force generates shaft power that operates the pump, and then the air gets vented and the diaphragm moves back, and we continue this process back and forth. And in this case, we've got dual diaphragms, one on either side, so we can speed up and smooth out the delivery of shaft power to the pump to make this operate. But you can get into the details of it if you wish, but the general concept here is that we're using compressed air to pump some sort of a fluid, or it could be a slurry, a combination of solids and liquids. We see diaphragm pumps used in that regard. And we just have to convince ourselves that this really is required, the compressed air diaphragm pump, as opposed to some sort of a motor-driven pump that might be able to accomplish the same task more efficiently. Baghouse type bag filters are often cleaned with pulses of compressed air from nozzles and a header piping system that delivers the compressed air to an appropriate location on each particular bag. There's different ways to control the timing of these pulses. Simple control systems will simply pulse the bag on a time clock and say, okay, once every 20 minutes we're going to pulse this bag whether it's dirty or not. Better, more efficient, more sophisticated control systems will actually monitor the pressure drop across the bag and have a set point when we have collected enough particulate on the bag that the pressure drop increases to a certain level. Then it's time to pulse the bag and clean it. And this can, during periods of reduced load or sometimes no load at all, this can save us a lot of compressed air. It's a really good idea. It also extends bag life, as a major component causing bag failure is the actual cleaning process of it being pulsed with compressed air. Structurally, over time, can wear them out. And there's the last point on the slide just is that we need to have some logic that keeps us from trying to clean or pulse rows that are right next to each other, because that's going to stir up some of the particulate into the air around the bag, and we can simply re-entrain that. So if we would have enough intelligence in the pulsing logic that we pulse one on one side, one on the other side as far away as possible, kind of move around in that fashion, we'll keep the bags cleaner longer by not capturing the same particulate twice. This slide reiterates the previous discussion and shows a picture of some filter units that utilize baghouse type bag filters. And again, another thought here is that acoustic cleaning of filters can actually replace compressed air pulses. And so there are what they call acoustic horns that can be used. And for some applications, not for all. So that's something that you could look into. And so it might be possible sometimes to completely eliminate the use of compressed air for bag cleaning, and that would eliminate the differential pressure pulsing, as well as we would, of course, rather, if we're going to pulse, we'd rather do it on a differential pressure measurement. But the use of acoustic horns and acoustic cleaning devices could well let us eliminate the use of compressed air completely for this application. This slide refers to the installation of solenoid valves in the supply line to a particular process, a line, or even an individual machine that might have a good number of compressed air fittings that might be prone to leaks. And so if the machine has a general on-off switch that when we're not using the machine, we hit an off button and that cuts the electricity to the machine, we could tie a solenoid valve into that and install that solenoid valve in the compressed air supply line. And when the machine is down, the solenoid valve would shut and we would depressurize the compressed air line, and so we would not be feeding leaks the entire time that the machine was off. Now, if a machine runs 24/7 pretty much all the time, there's not much to be saved here. But if we have machines that may be on and off, not even run all day during a regular production day, and then are off on Saturday and Sunday, and sometimes processes are down on Friday if business is slack, this is a way to really knock down the leak flow from compressed air leaks. So it should be considered anytime we have a large system and we struggle to keep really good control of the compressed air leaks. We're referring here back to different types of condensate drain traps for the removal of moisture from the compressed air piping and distribution system, and this just reminds us that the timed drain traps are basically a compressed air leak on purpose. We went through the meaning of the two different dials and the two different dial settings, but basically this trap will open every 15 minutes and stay open for 15 seconds every time that it does open to move moisture from the system, whether it's present or not. A more intelligent trap would simply fill up with moisture and open when it reached a full condition, expel that moisture down to a minimum level, and waste no compressed air in the process. This slide is looking at the control of compressed air use. And in a lot of different applications, we may have a conveyor system, and we may be blowing compressed air, from onto a product. This can be sheet steel, rolled aluminum. It can be individual parts. There's lots of different applications for this, and the idea here is we have a pipe. We have some sort of series of nozzles that are directing compressed air onto the parts that are on the conveyor. If you don't have some sort of a control system, you would simply blow compressed air continuously, whether the parts are present or not. And so what this system, this particular one, is manufactured by X-Air. There's a lot of good companies that manufacture components in the compressed air industry to allow you to become more efficient. This just happens to be one that I have stolen some product literature from. But this has a photo eye which looks to see if a part is present or about to be present. The photo eye can be installed a little bit upstream, and when a part is coming, there's a quick acting valve that opens up, and we supply compressed air to blow off the part for whatever function, whatever reason that's necessary. And as soon as the part is no longer present, we can do this on a timing, or we can do it on a second photocell. Then the compressed air nozzle or valve shuts, and we de-energize the airflow. And there are lots of times with production lines that the line will be stopped for some particular reason, and you can tie that into it to make sure that you simply don't just continue to blow compressed air needlessly when you're not producing any parts or when you're not moving anything across the line. Or also that would work on weekends and when the overall production facility might be down as well. This slide takes a quick look at induction nozzles, which can be used on open blowing applications to significantly reduce the amount of compressed air that we consume. The idea is that if you have a wand or an open pipe that we're blowing compressed air out of for a particular application, we can install a nozzle, and the nozzle has very small holes that allow some compressed air to pass through it and out at the tip at a very high velocity, much higher than would be present without that. And that high velocity flow out those small holes will induce ambient air just around the nozzle through the chutes on the side. And the net result is we get about the same flow at the end of the nozzle out 2, 3, 4, 5 inches. We get about the same flow pattern with about the same flow rate, but we use only a fraction of the compressed air to achieve that. Now, issues, and another good point of this is that drastically reduces the noise level caused by blowing compressed air out of an open tube. So that's another good reason to look at the induction nozzles, not only for the reduction in cost by reducing the compressed air, but also it will drastically reduce the noise levels. A couple of notes here. If you have dirt and debris inside your compressed air system, perhaps you have some corroded fouled pipes, and that exfoliates small particles. They can get down into these small passages inside the induction nozzles and clog them. So that can be an issue. It's possible to put a filter, or if you're going to put a bunch of these on fed by a main line, you could put a filter in the main line right before the nozzles to remove those particles. And then, of course, we're inducing ambient air around the nozzle into that flow. If you have any contamination, dust particles or aerosols or fine droplets in there that you don't want to blow back on whatever item that you're directing the compressed air onto, that could also be an issue. So they don't work in every application, but a lot of times it's a really good project and can pay for itself quickly. The basic nozzle is in the $40 to $50 range, and they should last a long time unless they become clogged or somehow otherwise damaged. One additional induction product would be an air knife, and an air knife would be if you want to blow all the way across a fairly large area in a linear pattern. You can install the air knife, and it works in the same way that the nozzles do. We direct a fairly small flow of compressed air at very high speed out the center of the air knife, and it induces air, as you can see in this photograph that joins in the flow. And so we get a much larger amount of air flowing out onto our product that we would if beyond just what the compressed air that's used. It's pulling a lot of ambient air with it, and that can significantly reduce the amount of compressed air it takes to blow off the product, saving us significant amounts of money. Here we're looking at an additional slide detailing the air knife. This is the X-Air Super Air Knife model, but you can see it can be used to clean, dry, blow off dust, debris. It's advertised to be quiet at only 69 decibels. The air amplification is 40 to 1, which is significant, and we get a uniform air curtain that will blow across our produce or our product as it flows under or moves under the air knife. Okay, in this slide we have a compressed air system improvement example from a recent project. This was a spring and stamping plant. The system was comprised of 100 horsepower and 125 horsepower rotary screw lube injected compressors, and the big problem is we can't make enough air, and so you've got to do something. Either a typical solution would be to add another air compressor and just up your cost of operation. However, if you can go in and perhaps do a project or a series of projects on your compressed air system to reduce your air use, that might overall have a better economic impact on your plant's operation. So the energy efficiency measures implemented here were to fix leaks, replace the old time condensate drain traps with zero loss traps, and add some storage to allow the compressors to stay unloaded longer, or the trim compressor to stay unloaded longer when it unloaded. Replace the Venturis with vacuum pumps. Don't generate our vacuum with compressed air. Install intermittent air controls and nozzles. Let's shut things down. Turn off open blowing applications when there's no product present. And let's add solenoid valves to cut off the air supply to idle machines. When the machine is powered down, the solenoid valve shuts, and there's no way to feed leaks downstream of that solenoid valve. So what was the result of all this? The savings turned off the 125 horsepower compressor and negated the need to purchase a new compressor. Significant. Saved $72,554 per year with a $62,845 investment. It's about a 0.87 year simple payback, and avoided maintenance on the old and proposed new compressor, as well as capital cost on the new unit. So this was considered a very successful project. We have a summary here of a second improvement example. This would be an aircraft parts manufacturer. The system was a 75 horsepower and two 100 horsepower lube injected rotary screw compressors. The system runs inefficiently and does not maintain pressure. The energy efficiency measures implemented were, and this was somewhat similar to the previous one, but we fixed leaks, replaced the time drain traps, condensate drain traps with zero loss traps, and we added storage. Install a smart sequencer master control panel to select the mix of compressors to run, to determine which compressor should be base loaded, which should be the trim compressor, and to monitor overall run times on the compressors to give us some intelligence in the sequencing and dispatch of the compression assets. Replace blow-offs with air knives and nozzles. Reduce artificial demand. That means let's reduce the pressure on the system. Again, artificial demand occurs when we operate a system at a higher pressure than it really needs to, and that higher pressure forces more air out of every open blowing application and leak. That's what we mean by artificial demand. Install new cycling thermal mass refrigerated air dryer to provide a better quality compressed air to the system and better manage the moisture in the system. Savings, we're able to turn off a 100 horsepower compressor and the 75 cycles intermittently on the new master controller. Saved $87,120 per year with a $108,557 investment and a simple payback of 1.2 years. We'll now move into the final section of the workshop, which just has a variety of comments intended to summarize a lot of the information that's been presented here. It's a great idea to create what we call a baseline on your system before you start an energy efficiency campaign and trying to reduce your operating cost, to let you kind of know where you are when you start. And then after you complete each measure, it's a good idea to redo the baseline to evaluate how successful you've been and then to help you plan future projects. So what do we do when we create a baseline? Well, we should do things like measure power, energy, flow, pressure, and leak load. That will help us evaluate, well, what are we paying now? How efficient are we? How much air are we leaking, etc. Estimate energy consumption and correlate to production levels. If production goes up 25%, do we really make any more compressed air, or does it seem to make much of a difference? How does that correlate? Maintain compressor and system pressure at lowest possible levels. Depending on compressor types, the rule of thumb is 2 psi can equal 1% compression energy for the lubricant injected rotary screw. The lubricant free compressors, that's certainly true. Pretty much true on the reciprocating as well. Centrifugal compressors, that's not necessarily doesn't follow, because those are dynamic compressors. They operate more like a fan than a displacement type air compressor. We would like to avoid as much as possible part load operation, which most of the time is fairly inefficient. If we've got a new variable speed compressor, however, we've taken a good step to mitigate the inefficiency at part load. Measuring temperature can help you maintain your compressors. When temperatures inside your compressor at various stages start to wander, typically they will increase when you start to develop problems. So by monitoring those, you can have a pretty good idea of the health of your air compressors. Record all measurements when the system is new. That's a super idea. That way you can say, well, gosh, I'm measuring a particular temperature to be this today. You know the temperature of the day, the ambient around the compressor, all that sort of thing. But what was it, 2 years ago when you had a brand new compressor sitting there? Gives you a real good set of information to compare to. It's also a good idea in creating a baseline to be able to record some data and like pressure, current flow, or kW used by the air compressors, flow rates in the system. It's wonderful to have compressed air flow meters, at least on your overall system, if not even some large branch lines. And then be able to record that data and plot it out for a day, several hours during the day, for a week, whatever, and compare at different production levels and from 1 month to the next month to the next month. It gives you a really good detailed information on what's going on in your system and really enhances your understanding of the operation of your compressed air system. If you're about to start a new energy efficiency campaign on your compressed air system, but you don't really know where to start, well, here's just a slide with some bulleted items to give you some ideas to get you moving a little bit. So simple steps you can take are the following. Just walk through and look for low-hanging fruit, obvious measures that you can accomplish. Reduce compressor discharge and system pressures. Give it a hard look. Take some measurements out towards the end of the system. If you have any areas that tend to be sensitive, more so to compressed air pressure than others, you might put in some pressure gauges out there. If you don't have them, put in some logging pressure gauges where you can record that data every second for 24 hours. Look and see how that pressure is fluctuating over the course of a day. Figure out what pressure we need at those sensitive locations. It could be that you could change out a component, you could change out a cylinder, put in a larger diameter cylinder in a couple of instances, and reduce your overall system pressure 5 or 10 psi, which would have a tremendous payback. So you have to think about these things. You can start slowly reducing compressed air pressure a couple psi at a time and see who develops a problem, and then try to diagnose that particular problem, solve that one, and then continue reducing the pressure. Eventually you'll get to a point at which you just can't go any lower. There's too many applications out there that require a particular base pressure, and then you need to probably step a couple of pounds above that. And then make sure you don't have too much fluctuation in the system, which could perhaps be improved by the installation of storage. Look for and reduce compressor part load energy waste. We spent a lot of time looking at how air compressors load and unload and the efficiency of those, so you would need to look into implementing some of that in your plant if you think there are opportunities there. Maximize the efficiency of air treatment. You don't want to filter or dry the air to any point beyond which is absolutely needed for your process and equipment. It just costs more money to make it drier and make it cleaner. So you have to evaluate. And if you have one or two particular uses that require very clean air, the rest of the plant doesn't require air nearly to that standard, you might look at some point of use conditioning to make those particular the compressed air to those particular uses much higher quality, and let the rest of the plant air be at a lower quality, which would reduce your operating cost. Certainly, repair leaks, fix hoses, replace inefficient condensate drains, eliminate inappropriate uses. We've been through all that in some degree of detail. Turn off unneeded air compressors and treatment equipment. If you do a good leak program, the best you can do is to be able to turn off an air compressor. There's tremendous savings in that. Performance improvements to a compressed air system can take many forms. We have a list here that spells out performance EO as you look down the bold letters on the left-hand side. At any rate, pressure reduced at source, that would be at the compressor. The source would be where we're generating the compressed air, and we've got a pressure setting on the compressors. We've mentioned several times in the workshop that if we can reduce the pressure on common types of air compressors, rotary screw and reciprocating, that we get roughly a 1% reduction in compressor energy for every 2 psi. We set that discharge pressure down. External intake, that would be of inlet air for reciprocating and dry screw compressors. It's typically better to have cooler intake air, and sometimes it can be cleaner if we take it from an external source. Reduce pressure at point of use. If we can do anything to reduce the pressure requirements, perhaps changing out air cylinders, actuators to have a larger diameter, which means they can deliver the same force with less compressed air pressure, we can move in the direction of operating the entire system at lower pressures. Fix leaks, we talked about that. Always good to fix leaks, but the money saved at the compressor, so we've got to translate the reduced leak flow into actual electrical savings at the air compressors. Optimize pipe size and receiver storage. If we have certain sections of compressed air piping that are carrying too much air, have too high velocities, we might want to consider replacing the pipe with larger diameter. And the savings would be back at the compressor by being able then to run a lower discharge pressure. Our design number is 20 feet per second velocity. It's acceptable up to about 30 feet per second, and much above that you'll see that the pressure losses become excessive if we have any significant length of pipe seeing those velocities. Heat recovery, that's always a good idea. On an air-cooled machine, we've got to duct the air to some point that's going to reduce our operating cost. It could be for space heat. We get 4 or 5 months out of the winter that can reduce the load on the plant heating system. If we can use that heat in a process, we could use it all of the time. You could blow that hot air into a boiler for the combustion air, and because it would be coming in much warmer than the ambient air, that would reduce the gas usage on the boiler. If we're going to use it for plant space heat, we're going to have to throw it away in the summertime most likely. Water-cooled machines, we have the potential to run our cooling water through there, pick up a lot of the energy into the compressor, and then take that to some sort of a usage where that heat having that water preheated will save us energy. Maintenance must be excellent. We have to maintain these compressors and the filters and the dryers and our compressed air system to get the optimal efficiency out of it. Audit uses continuously. If you're not measuring, you're not managing. So you have to keep a pretty good watch on your pressures, your currents, to check your unloading strategies on the compressors, make sure that's right, etc. No unnecessary compressors operating. We certainly would not want to run 3 compressors at half load when we could get by with 2 compressors, or you just want to minimize the number of air compressors running. All running or fully loaded except one trim machine is the rule of thumb. Calibrate all measurement recording instruments. If you don't do calibrations, after some period of time the measurements won't mean anything. Explain cost, eliminate excuses. We need to be able to understand where our money is going that we're spending on the compressed air system, and be able to assure ourselves and managers that that's a necessary expenditure and it has been minimized as much as possible. Eliminate unnecessary pressure losses from the system. Any filter elements that are clogged need to be changed. Anything in the system, if our piping is less than optimal, we may want to look at modifying some pipe joints or intersections in order to reduce pressure loss. And optimize moisture removal from the system. We've got to get the moisture out of the system, and we would want to do that with the most efficient compressed air moisture condensate removal traps that we can use. Those would be zero loss traps. They do cost a little more, but in the long run, it will pay off. The investment will pay off. Here we have some additional suggestions for efficient operation. On replacement parts, it's a good idea to use the manufacturer's OEM parts. You start using other brands. Sometimes they're not equivalent and they're not of the same quality. Dirty intake filters reduce efficiency, so keep them clean. Certainly that's where the air would enter the system, and if we allow those filters to get really dirty, then they get significant pressure drops across them, and that increases the work that the compressor has to do in order to provide the same discharge pressure. Dirty oil filter can affect reliability and durability. Change them according to instructions. That pretty much speaks for itself. Test and change lubricants per instructions, especially with extended life synthetic lubricants. Taking oil samples and sending them out to the lab periodically will give you a very detailed picture of how your compressor is operating. That's really a good idea to do. Keep coolers clean. We've got to be able to reject the heat. The aftercooler has to work properly in order that's the majority of the moisture removed from the compressed air is in the aftercooler. So all the coolers, the heat exchange surfaces have to be kept clean. Maintain a clean, cool compressor operating environment. We will derate dryers. We saw that if they're above 100 degrees ambient in their operating environment. Also, we need to keep the operating environment temperatures down on the air compressors to allow them to operate efficiently and to minimize maintenance expense. We have a couple of slides following this one that give some information relating to compressor selection and sizing. We'll now discuss a number of items related to compressor selection and sizing. The first would be understand your system demands and flow characteristics before selecting an air compressor. You really need to understand your maximum load, your minimum load, your load variation, your required pressures, how tightly that pressure needs to be controlled, what is your air quality in terms of particulates, vapors, liquids, etc. So that would lead into your dryer selection type and pressure drop across the dryers. So you need to have a lot of knowledge about the requirements of your system before you step out and start considering what compressor or compressors should be purchased. Total kW input and or specific power over the full operating range must be analyzed for a proper comparison with other types of capacity control. Part load operation, the variability of your load, and how your trim machine is going to respond to that are critical in establishing the efficiency of your compressed air system. No compressor is perfect for every system. So the characteristics that you determine in the first bulleted item above and the consideration of the part load strategy will lead you to the selection of the appropriate compressor. Reliability and durability should be considered. Absolutely. A system that has compressors down on a fairly regular basis, it's going to be difficult to maintain production and cause a constant headache to maintenance staff as well as production staff and engineering. Many demands are intermittent, but the worst case scenario must be considered. So what's the maximum amount of air that we might ever be asked to produce at any one time? We probably need a safety factor put on top of that. And what's the minimum pressure that we can accept that will allow processes and systems in the plant to operate appropriately and properly? That all needs to be determined on the front end. Need backup compressor or compression capability to cover the largest air compressor. So Murphy's always lurking in the surroundings. So whatever the largest air compressor you have that normally operates, you need to have that much compression capacity on standby or in reserve, not operating, so it could be turned on if you lose your largest compressor. That backup capacity also refers to dryers as well. Consider multiple compressors networked together for multi-shift operations. That's a good idea. You may have a few more smaller compressors, but if you lose one, then your backup compressors don't have to be as large. If you have a master controller or a smart sequencer that can dispatch these compressors and rotate them and establish the best trim compressor for a given load range, these can be quite efficient and effective systems. We are continuing our discussion of compressor selection and sizing. Centrifugal and rotary screw compressors are better suited for continuous base load type service. Centrifugal air compressors are wonderful base load machines. They produce oil-free air. They're very efficient, and you can turn down to approximately 75% of rated capacity with inlet guide vanes, and that's a very efficient unloading strategy. When we get the inlet guide vanes to their minimum position, to reduce airflow anymore requires a blow-off valve operation typically, and that's very inefficient. So keeping centrifugal compressors base-loaded, they're wonderfully suited for that and should be considered. The rotary screw also work very well. Rotary screw compressor with a variable frequency drive capacity control is an excellent part load compressor. We saw that in the comparison of the unloading curves, and VFD, variable speed machines, are wonderful trim machines. They're optimized. The screws are most efficient in the 40 to 60 to 70% load range. That's where they would be expected to operate, and it's a really good compressor to use for a trim machine. Small single-acting reciprocating compressors are excellent for small plants, as well as small high-pressure applications in a large plant. A lot of auto repair shops, really relatively light compressed air loads, they do wonderfully with the single-acting reciprocating with a decent-sized storage tank. Or in a large plant, you may have just a couple of compressed air uses that require a much higher pressure than the rest of the system. So it makes a lot of sense to supply those small loads with small single-acting reciprocating compressors. They may be 3, 5, 10 horse, something like that. You may have to boost the pressure to 125, sometimes 150 pounds for a particular application, the way a machine has been designed. But it would be very wasteful to have to operate your entire system at that high pressure. Consider increased storage air receivers. More storage is always better. You can't have too much receiver capacity or compressed air storage capacity in a system. It helps smooth out load fluctuations. You have a large storage tank, you get a short-term, intermittent, large use of compressed air opens up. Instead of pulling down system pressure, it simply pulls some air out of a large storage tank, and the system pressure sees virtually no fluctuation whatsoever. The storage tanks also allow lube-injected machines to stay unloaded long enough that you get the benefit of the efficient unloading. We need to keep those machines unloaded about 2 minutes at least on the unload portion of their cycle. Understand your system demands and size your compressor to match. You have to know what your peak demand is that you're going to have to meet on a regular basis or even just a short-term basis, and design your system around that. Consider reasonable growth, but don't oversize for something that may not happen. Sometimes we put in a huge air compressor thinking that we're going to add additional lines in 2 or 3 years, and that never happens. And so then we're saddled with a compressed air system that's difficult to operate efficiently because the compressors were not sized for the current load. We have a quick example here of calculating the annual energy usage and cost from electrical current and voltage measurements. So in the example, we see that our average electrical draw on the compressor is 250 amps. The voltage is at rated 460. The 1.732 is the square root of 3, and that's in there because this is a 3-phase load. Our power factor is estimated at 0.85 or 85%. Compressor operates 6,000 hours per year, and electricity costs 10 cents per kilowatt hour. Of course, we divide by 1,000 because otherwise we would have units of watts in the calculation. So dividing by the 1,000 gives us kW times hours is kilowatt hours times 10 cents is the rate, and all that produces a number of $103,613 per year to operate this particular air compressor. We now have an equation here that will convert brake horsepower to annual energy cost. And the brake horsepower is the actual horsepower that's delivered into the shaft of the motor. So that's the output power from the motor that's driving the air compressor. Most compressors use part of a service factor designed into the motor. What that means is a service factor on an electrical motor is often 15%. So for example, if we had a 100 horsepower motor, its rated output at full load is 100 horsepower, brake horsepower. If we have a 15% service factor, that means that motor can be operated at 115 brake horsepower for fairly long periods of time without doing damage to the motor. Now, caveat would be we'd have to make sure the motor doesn't run at elevated temperature, which means that the ambient conditions around the motor would need to be relatively cool, at least at or below the temperature rating on the motor. So that is called designing into the service factor when you take a 100 horsepower motor and design your compressor at peak full load to pull 110 horsepower. So that's what that comment is referring to. Then as we look at the equation, we have the brake horsepower, the output of the motor, and if we multiply that by 0.746, that converts us to units of kW from brake horsepower. Then we would have to multiply that by the number of annual operating hours. So that would be kW times hours would be kilowatt hours, and then we need the kilowatt hour rate. Say in the previous slide we used 10 cents per kilowatt hour, and we have to divide by the motor efficiency because the motor actually pulls more power than the output energy because of the inefficiency of the motor. So if the motor is 95%, we would divide by 0.95, and that would account for the motor losses. We'll work a quick example here. And so for the example, the air compressor we're looking at is a 100 horsepower unit, and it is operating at full load into the service factor, and the motor is outputting 110 brake horsepower. The motor efficiency has been determined to be 93%. This compressor operates continuously, or 8,760 hours per year, and the electrical rate is 10 cents per kilowatt hour. We're now going to finish this little example problem of converting brake horsepower to annual cost. The numbers given on the previous slide are inserted into the equation, and we see we have 110 brake horsepower. It's multiplied by 0.746, which is the conversion from brake horsepower into kW, then multiplied by the number of hours of operation. That would then get us kilowatt hours per year, and then we have a cost of 10 cents per kilowatt hour, and we have to divide by a motor efficiency of 0.93 because the 110 brake horsepower is output energy from the motor, and we need to account for motor losses, which it's about, we're losing about 7% because of inefficiency in the motor, heat losses, friction, windage, etc. So we divide by 0.93, and that gives us an annual operating cost of $77,295 for this particular motor. And we should note that this is a full load calculation, does not include the correction for part load, and the fan brake horsepower for air-cooled compressors is also not included here. We're now going to make a few summarizing comments here. It's obvious from all of this and your experience in life that compressed air is important to the operation of an industrial and manufacturing facility. Compressed air systems start with the supply side. If you don't have an air compressor operating, you're not going to have any compressed air, that's for sure. Compressed air systems go much beyond the compressor room, however. We have conditioning to consider. We've got to distribute the compressed air out to the end users, and we've got to utilize it effectively. Baselining is essential to manage a compressed air system. You need to know what the system looked like and how it operated and its characteristics when it was new. You need to do it on a regular basis as a point of comparison. Compressed air systems can be controlled, must be controlled, and we must do that efficiently. Looking at the part load operation of the compressors is a great place to start. The efficiency of a compressed air system can be maintained, but we have to look at it, we have to take measurements, and we have to be critical in evaluating its operation. By developing and implementing a plan, you can ensure that your compressed air system is efficient and cost effective. This is not going to happen by itself. It takes a concerted effort to keep a compressed air system operating at peak efficiency. At long last, we've come to the end of this workshop on compressed air efficiency. I hope that you have enjoyed it and learned a good bit from going through the slides and listening to the description provided here. If any questions arise, I can be contacted at my email address at Tennessee Tech University. That is Cunningham, Cunningham at tntech.edu. Please email me and I'll do my best to respond in a timely fashion. If I don't know the answer, I will go search around and find somebody who does. So I hope you enjoyed the course, and let me hear from you if I can be of any further assistance. Thank you.